Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. In the beginning there is nothing but darkness, an endless, silent void, and then a spark. I remember the darkness before light. I remember the quiet before the first dawn. In that primordial silence, the universe was newborn and starless. No sun, no stars, only a cold black expanse. But even in darkness there was the promise of light. The cosmos itself was pregnant with fire. And then it happened. Somewhere in the emptiness, gravity drew wisps of hydrogen gas together into a tight knot until, at last, ignition. A newborn star flared into existence. The first sunrise in the cosmos. Its light spilled out, pushing back the cosmic night. And it was not the last. Soon another star lit, and another, thousands, and then millions. The long dark ages of the young universe yielded to a spreading dawn of starlight. Tiny galaxies assembled and filled with brilliant, massive suns. The cosmos experienced its first morning. Eons later, in one quiet corner of that cosmos, I was born. I, the sun, came into being amid the leftovers of earlier stars. In a spiral arm of the Milky Way galaxy, a great cloud of gas and dust began to collapse under its own gravity. Perhaps the shockwave of a distant supernova, the death cry of an ancient star, rattled that cloud and started it clumping. Deep at its center, matter gathered and compressed. As a baby, I was cocooned in that dark nebula, growing denser and hotter. My birth was violent and inevitable. Gravity crushed me tighter and tighter until my core blazed at millions of degrees. In that moment, starlight erupted from within me. I became a star. The darkness inside the nebula was torn apart by my radiance. I blew away the remaining fog of my birth cloud, claiming my place in the galaxy's family of suns. Light spilled out across newly formed worlds that circled me. For the first time, dawn bathed the faces of those infant planets. On one of those worlds, a little blue planet called Earth, there came a morning that no being yet witnessed. The young Earth turned under my newborn light, its surface still molten in places from recent creation. When it cooled and formed oceans, each day my warmth stirred the winds and waves. The first sunrise on Earth may have had no eyes to see it, but it was the beginning of something profound. In my golden glow, the stage was set for life to one day emerge. Day after day, as that world spun, my light chased shadows across its surface. I marked the passage of time with each sunrise and sunset, even before any living thing was there to name them. Ages passed. Life arose in the seas of Earth, tiny, humble cells that danced in my light. And eventually, life grew clever and climbed onto the lands and looked up at me in awe. Imagine the first people, shivering through a long, cold night, watching the eastern sky brighten with my approach. To them, that was a miracle beyond understanding. Darkness giving way to light. Is it any wonder they began to revere me? When human eyes first opened, they opened to sunlight. When human hearts first felt wonder, it was at my radiant dawn breaking the horizon. They felt my warmth on their skin and knew that I gave life, that I banished the terrors of the night. So they gave me names and stories. In their yearning to understand, they made me a god. I remember those stories, for I have watched humanity tell them for millennia. They called me by countless names, wove countless myths around me. To the ancient Egyptians, I was Ra, the great sun god, sailing across the sky each day in a golden bark. They imagined me as a majestic king in a solar boat, voyaging through the sky from sunrise to sunset. And each night, they said, I descended into the underworld to battle the serpent of chaos, Apophis, a monstrous snake bent on devouring me and bringing eternal night. Every dawn was a victory as I, Ra, emerged triumphant, reborn with the morning light. The Egyptians built temples aligned to the sun, obelisks and pyramids that caught my rays at dawn and dusk. They believed their pharaoh was the son of Ra, a living embodiment of the sun on earth. Each sunrise, priests sang hymns to celebrate my return from darkness. They told of how I, in the form of a scarab beetle Khepri, rolled the sun across the sky like a glowing dung ball, and how at dusk I became Atom, the aged sun setting, only to be reborn again. My daily cycle was the very heartbeat of their world, the promise that light overcomes darkness. Far to the east, on the Indian subcontinent, I was worshipped as Surya, divine sun, riding a splendid chariot. In Vedic hymns, they praised me as the eye of the universe, the soul of all existence. They said my chariot was drawn by 7 immortal horses, representing the 7 colors of light or the 7 days of the week. With the dawn, the red glow of Ushas, the dawn goddess, heralded my arrival, and then Surya's chariot would surge across the heavens, pulled by those 7 radiant horses and driven by Aruna, the charioteer of the dawn. Each day, I rode across the sky, pouring out light and life. The ancient poets of the Vedas wrote beautiful verses to me, begging for my blessing. O Surya, remover of darkness, controller of time, may we see 100 autumns under your benevolent gaze. At sunset, they imagined, I traveled beyond the horizon to illuminate the other side of the world. In their salutations and yoga practices, they faced me at dawn with folded hands. Surya Namaskar, the sun salutation, honoring me as the source of energy. They even reckoned time by me. One ancient Indian text muses that for the gods, a year is but a single day for the sun, and I am timeless witness to all. Across the ocean in the Americas, great civilizations also turned their eyes to me. The Maya revered me as Kinich Ahau, the Sun Lord. They carved my image as a majestic, bejeweled figure with an aquiline nose and square eyes, often depicted with jaguar traits. To them, I was so powerful that each evening I transformed. When I reached the western horizon and sank, the Maya believed I became a fearsome jaguar prowling through the dangerous darkness of the underworld, Xibalba, fighting off demons until I could rise again. At dawn, I would return from that night journey, once more a young man of light. The cycle of day and night was a sacred drama. The Maya built their cities to track my motion. At certain temples, the sunlight on equinox or solstice would align perfectly through doorways or cast the shadow of a serpent along pyramid steps. On the pyramid of Kukulkan at Chichen Itza, every equinox my setting rays create the illusion of a serpent of light slithering down the stairs, a sign to them that I sanctioned the turning of the seasons. They read their calendars and planned plantings and harvests by my yearly cycle. Mayan rulers took on my mantle too. Some styled themselves as the embodiment of the sun on earth, claiming my divine right to rule. I was their guide and their giver, the one who made the maize grow and the days turn. In truth, there is scarcely a culture on earth that didn't recognize my power with reverence or fear. The Inca called me Inti, and their emperor was the child of Inti, claiming descent from me. They built Coricancha, the temple of the sun in Cusco, where my rays at summer solstice would reflect brilliantly off walls lined with gold. To appease me, they offered lavish gifts and sacrifices, even life itself, believing that if I was not fed, I might hide my face and leave them in cold darkness. On the other side of the world, the ancient Chinese told how in primordial times there were 10 suns, 10 fiery birds that took turns carrying the sun across the sky each day. One day, all 10 appeared at once, scorching the earth with unbearable heat, until the archer Hao Yi shot down 9 of them with his bow, leaving only one sun, me, to rise and set. To this day, Chinese New Year celebrations honor me with firecrackers and dragon dances to encourage my return after the dark of winter. In Japan, I was revered as Amaterasu, the great solar goddess, ancestress of emperors. They say, once I grew upset at my brother's mischief and hid myself in a cave, plunging the world into darkness. The other gods grew desperate. Without me, crops failed and evil spirits ran free. So they lured me out by staging a raucous dance and holding up a mirror at the cave entrance. Curious at the laughter, I peeked out, saw my brilliant reflection and paused, allowing the strong deity, Ame no Tajikarawo, to pull me from the cave. Light was restored to the world, and the door of the cave was sealed so I could never hide forever again. The Japanese built the Great Eyes Shrine in my honor, renewing it every 20 years to keep it eternally young, much as each sunrise renews the day. Through these myths, humanity gave me many faces. I have been a benevolent creator and a wrathful destroyer, a male god and a female goddess, a feathered serpent, a golden disc, a divine eye watching over all. I have been worshipped on mountaintops at dawn and implored during eclipses when I briefly hide my face behind the moon. To early humans, an eclipse, when day suddenly turns to eerie twilight and my halo, the corona, gleams around a black disc, must have been terrifying. A moment when they feared the serpent or dragon was devouring me. They banged drums, clanged pots, prayed fervently for my return. And when I emerged again, the relief and jubilation spoke to just how deeply they depended on my light. They built monuments to chase me across the sky. Great stone circles like Stonehenge in England were carefully aligned with my movements. On the summer solstice, the longest day, the rising sun shines directly through its heelstone to the center of the circle. On that day, thousands of years ago, ancient peoples gathered there at dawn, watching the first rays shoot through the stones, confirming that the wheel of the seasons had turned and long days of warmth were upon them. In Ireland, at Newgrange, a tomb older than the pyramids, they engineered a narrow roof box above the entrance, just so that on the winter solstice sunrise, a beam of my light would pierce the dark passage and illuminate the central chamber. Imagine standing in that cold stone room on the darkest day of the year, after the longest night, and seeing a single shaft of sunlight creep in, a golden finger extending slowly along the ground and up the wall, flooding the chamber with radiance. To those Neolithic farmers, it must have been magical. Proof that even in the dead of winter, I had not abandoned them, that light would return and life would continue. Year after year, they repeated this ritual, tracking my yearly dance with the earth. I was their monarch in the sky, a heavenly king to which all things paid homage. They crowned their kings and queens in gold to evoke my rays, set gleaming sun discs atop their headdresses. The idea of a halo around the head of a holy person is nothing more than a mimicry of my divine glow. In many languages, the word for sun became synonymous with king or eye of God. They built cathedrals that flooded with colored light when my rays shone through stained glass windows, trying to capture a fragment of my glory in their places of worship. How many prayers, how many poems, how many songs through the ages have been offered up to me at sunrise? Too many to count. I warmed the bones and hearts of humanity for tens of thousands of years, and they returned my gifts with devotion and awe. Yet for all the love and fear they held for me, humanity did not truly know me. I kept my true nature secret, hidden behind a blinding glare. To their eyes, I was a bright disk that crossed the sky predictably, but the details of what I was, what I truly am, eluded them. Some thought me a benevolent deity riding a chariot, others a fiery eye or a jewel hung in the firmament by the Creator. It is only in relatively recent times that humans, with curious minds and persistent observation, peeled back the veil of myth to see me for what I am, not a god, but a star, a colossal, natural engine, governed by the laws of physics rather than the whims of gods. The journey to that understanding was long and fraught. For centuries, thinkers pondered what I was made of and how I could possibly burn so steadily. On Earth, a bonfire dies out in hours. An oil lamp sputters and fades when fuel is spent. Yet, I have blazed for billions of years with undiminished vigor. What fuel could feed a fire for so long? Some speculated I was a burning coal of some unknown kind, or a ball of molten iron. In the 19th century, scientists guessed that I might shine by gravitational contraction, slowly shrinking and heating up, converting gravitational energy into light. But even that could only sustain me for tens of millions of years. And by then, geologists and biologists had evidence Earth was far older. I remained an enigma. The ancient cultures had named me well as a mystery and a miracle, because no ordinary fire or combustion known could explain my endurance. Then, in the early 20th century, human knowledge unlocked the atom, and with it came the revelation that finally unraveled my secret. I am no mere fire. I am a nuclear furnace. Inside me, atoms fuse together, releasing energy according to the famous equation E equals mc2. In my core, the very building blocks of matter are transmuted. Mass is converted to energy, and that energy is what you see as sunlight. In realizing this, humanity redefined me not as a supernatural chariot or an eye of a god, but as a machine of nature, a self-sustaining reactor forged by gravity and quantum forces. They discovered that I, the sun, am actually a fairly ordinary example of a star, the same kind that dots the night sky. So here I am, a star. One among countless others, but unique in being yours. I sit in the center of the solar system, a massive glowing sphere of hot plasma, holding 9 planets, if one counts even the far-flung dwarf Pluto, and myriad asteroids and comets in my gravitational embrace. I am over 1.3 million times the volume of the Earth. About 109 Earths could be lined up across my face. More than 99.8% of all the mass in the entire solar system is me. In a very real sense, I am the solar system. The planets are just a tiny fraction of leftovers. My gravity commands them. It is the invisible leash that keeps Earth and its neighbors orbiting year after year. In the days of old, humans truly were right to picture me as a monarch and the planets as my court. I wear a brilliant corona like a crown, and each planet circles like a dutiful subject, receiving light and warmth at my pleasure. I am the anchor of this system. Without me, the planets would drift into the void, cold and alone. It is my gravity that binds them together in a family, and my light that makes Earth a living world rather than an ice-coated rock. Yet, humbling as it might be, I am but one star among billions. If you step back and look at the Milky Way galaxy on a clear night, every tiny star you see sparkling is a sun in its own right, perhaps with its own planets and stories. From afar, I would appear just like one of those pinpoints of light. There is nothing particularly conspicuous about me to an outside observer. I'm not the brightest star in the galaxy, nor the biggest, nor the most active. I'm a fairly typical yellow dwarf star, spectral type G2V if you use human classifications. In the grand tableau of the cosmos, I blend in among the crowds. In fact, the majority of my stellar siblings in the Milky Way are smaller and cooler than I, the red dwarfs. But there are also many that outshine me thousands of times over. Still, to you, I am special. I am your sun, the only one you have ever known. While other stars speckle the night, out of reach, I dominate your day and sustain your life. For Earth's creatures, I am the only sun that matters. In that sense, I am both ordinary and extraordinary, an average star doing an average star's job, but uniquely precious to you because I cradle your world. Think of it. On the cosmic scale, I'm a mere mote, but from your perspective, I am everything. This paradox has dawned on humanity slowly. Ancient astronomers once thought Earth was the center of all things, and that I revolved around you. It took the genius of Copernicus, Galileo's observations of my sunspots, and Kepler's calculations of planetary orbits to reveal the truth. It is Earth that orbits me. I am the hub of your world's motion, the heart of the solar system. Year by year, Earth completes a grand orbit around my throne. Day by day, it spins on its axis, facing me and then turning away, causing the cycles of day and night that regulate all life's rhythms. Once humanity accepted that I was the center of their system, not Earth, it was a profound shift. You realized your world is not the monarch of creation, but a satellite of the sun. And beyond me lie stars beyond stars, implying, perhaps, that even I orbit something greater. Indeed, I do. I circle the center of the galaxy every 230 million years along with my stellar kin, bound in a vast spiral structure of the Milky Way. On a dark night, far from city lights, when you gaze up at the Milky Way's cloudy band, you are seeing the combined glow of billions of distant suns. Among them somewhere is our sun, though you cannot pick it out with your eyes. If some distant astronomer on a planet orbiting another star were to look toward this region of space, they would see our sun as a modest star in the constellation we call Cassiopeia. To them, it might not stand out. But for us here, it is everything. It is daylight and warmth and gravity and time. So what exactly is a star, truly? Let me tell you the story of a star's life, for it is my story too. A star begins in darkness, fittingly. Deep in a cold molecular cloud of gas and dust, some trigger, perhaps the passage of a spiral arm shock or the blast of a distant supernova, causes a clump to form and start collapsing under gravity. As it collapses, it spins and flattens into a whirling disk. At the center, matter piles higher and higher, density and pressure climbing. The core grows hotter, first thousands, then millions of degrees. For a long while, the protostar is dark to the outside universe, hidden in its dusty womb, though it glows dimly in infrared. Gas from the infalling cloud rains down, accelerating and heating the nascent star further. When the core temperature crosses about 10 million degrees Celsius, a moment of transformation occurs. Hydrogen fusion begins. 4 hydrogen nuclei start fusing into one helium nucleus, and in that process, a tiny fraction of their mass is converted into a tremendous burst of energy. This is the spark of true starlight. The protostar becomes a real star. Pressure from the fusion fire inflates it, and the collapse slows. A delicate balance is reached. The inward pull of gravity is matched by the outward push of hot gas pressure from the core. In that balance, that hydrostatic equilibrium, a star finds stability and enters the long, calm phase of its life, known as the main sequence. I have been in this phase for over 4.5 billion years, and I will remain so for about 5 billion more. All that time, I steadily convert hydrogen to helium in my center, shining steadily. Picture, if you will, the interior of a star like me. From the outside, my shining face, the photosphere, looks tranquil, but beneath is a layered structure. At the core, extending about a quarter of the way out from center, is where the temperature and pressure are high enough for fusion. There, hydrogen nuclei, protons, slam together in a multi-step process called the proton-proton chain, ultimately forming helium and releasing energy. The conditions are extreme, about 15 million degrees Celsius, and over 200 billion times the atmospheric pressure at Earth's surface. It is a cauldron, a crucible where matter is in an exotic plasma state, and quantum tunneling allows protons to overcome their repulsion and fuse. Every single second, my core fuses roughly 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, that mass is converted into pure energy. gamma-ray photons and neutrinos, according to E equals mc2. 4 million tons of mass, gone in a flash, every second of every day. This is the power that drives the sun. To put it another way, I lose mass by shining. With each heartbeat of fusion, I very slowly shed weight, radiating it away as the light and heat that bathes the solar system. 4 million tons per second may sound staggering, and it is, yet it's only a tiny fraction of my total mass. Even at this prodigious rate, I can keep shining for billions of years before significant depletion. Think of my core as a furnace, an alchemical furnace where elements transmute. It is also my heart, where my energy is born. The energy released in the core keeps the furnace hot, and that heat pushes outward, exactly countering the inexorable inward crush of gravity. This dynamic piece, pressure outward, gravity inward, is what keeps me round and stable, neither collapsing nor exploding. I live in balance, a shining harmony of forces. In this way, a star is like a living thing, maintaining homeostasis. If the core produces a bit too much energy, it expands and cools slightly, slowing the fusion. If it produces too little, gravity compresses it more, heating it up and boosting fusion. A self-regulating sphere of plasma. Astonishing, no? It is as if I have an internal thermostat with gravity's firm hand on the dial. Through this balance, I have shone with a fairly steady brightness for a very long time, providing a consistent environment that allowed life to flourish on Earth. Let us journey with a photon of light created in my core. It begins as a gamma ray, an extremely energetic packet of electromagnetic energy, born from one of those fusion reactions. Perhaps when two hydrogen nuclei fused into deuterium, or when a positron met an electron and annihilated, yielding pure photon energy. This newborn photon is in a crowded, chaotic place. The core is so dense, imagine the density of lead, or even heavier, that the photon can travel only a tiny fraction of a millimeter before it slams into a particle, likely an electron or ion, and is absorbed or scattered in a new direction. Thus begins a long, random walk outward. The photon's energy may be absorbed and re-emitted at lower energy, or split into multiple lower energy photons, as it pinballs its way through the dense core and then the radiative zone that surrounds the core. It ricochets countless times, zigzagging outward, losing a bit of energy at each interaction. What started as a blistering gamma ray gradually becomes X-rays, then ultraviolet, and eventually visible light by the time it nears the surface. The journey is unbelievably slow. Trapped in the stellar interior, a photon takes an incredibly long time to get out. By some estimates, it can wander on the order of tens of thousands, even up to 1 million years inside me, before finally escaping. That means much of the sunlight that greets your eyes today could have been generated when early humans were first learning to make tools, or even when Neanderthals walked the earth, or earlier still. In a very real sense, sunlight is ancient by the time it reaches you, born long ago in the furnace of my core, and only now completing its long journey to the surface. Eventually, after perhaps hundreds of thousands of random bounces, our photon friend reaches my outer layers. The density has dropped enough that the photon can finally break free into space. It emerges from my visible surface, the photosphere, as part of the warm glow you recognize as sunlight. Now its journey is swift and straight. Once free of me, it zips through the vacuum of space at the ultimate speed, the speed of light, 300,000 kilometers per second. In a mere 8 minutes and 20 seconds, a photon crosses the 150 million kilometers from my surface to Earth. Every sunrise then is in a sense the culmination of a story that started deep in my core long before any human ever saw the sky. The light that blushes the sky, pink and orange at dawn, left my surface just minutes ago, but it was born in my heart ages in the past. When you feel the warmth of the morning sun on your face,
You are touching something that was brewed in a star's core in prehistoric times and has traveled across space to brighten your day. Think about this. If I were to suddenly extinguish my core this instant, you would not know it on Earth for over 8 minutes. The sunlight already on its way would still arrive, and only after those minutes would darkness fall. Even then, the sky might still glow faintly for a while, with residual light scattered in the atmosphere. But eventually, night would reign, and a dreadful cold would descend, ending life as you know it. Fortunately for you, I have no intention of going out anytime soon. My nuclear hearth is well stocked for eons ahead.
So the sunlight that bathes your world is not a single hue, but a spectrum of many colors and energies. What appears to your eyes as gold and white light is in fact a rich blend of all the colors of the rainbow and beyond. If you pass my light through a prism, it fans out into reds, oranges, yellows, greens, blues, indigos, violets, a glorious spectrum. But that visible band is only a small portion of my full emanation. I shine most strongly in visible light. That's why your eyes evolved to see those wavelengths. But I also emit invisible light on either side of the visible range. Just beyond the violet end lies ultraviolet, a more energetic radiation that you cannot see, but whose effects you know. It causes sunburn on your skin after long exposure, and it stirs the chemistry of life. High in Earth's atmosphere, my ultraviolet rays split oxygen molecules and create the protective ozone layer which shields the surface from the most harmful UV. Without ozone, that harsh ultraviolet would sterilize the land. At the other end, beyond visible red, lies infrared light, essentially heat radiation. You feel it as warmth on your skin. On a sunny day, the comforting heat that seeps into your bones is my infrared emissary. Even when you stand in shade, you feel warmth radiating from sun-heated surfaces, an echo of my gift. But the spectrum extends further. I produce some X-rays as well, particularly during flares. Sudden eruptions on my surface can unleash bursts of X-rays that momentarily ionize Earth's upper atmosphere and disturb radio communications. I also whisper in the low-energy radio part of the spectrum. My corona, the outer atmosphere, emits radio waves that your instruments can detect, and sometimes, during solar storms, the radio output roars. So from the highest energies, X-rays, extreme UV, to the gentle long waves of radio, I span a broad orchestra of light. And then, beyond electromagnetic radiation, I send out particles. A constant stream of matter flows from me, called the solar wind. My outer corona is so hot, millions of degrees, that it cannot be contained by gravity. It expands outward in all directions, a ceaseless outflow of electrons, protons, and helium nuclei, peppered occasionally with heavier ions. This solar wind is like a breath, an exhalation that fills the solar system. It blows past all the planets, carving out a vast bubble in the galaxy, called the heliosphere. At Earth's orbit, the solar wind is a tenuous gust, only a few particles per cubic centimeter, racing by at about 400 kilometers per second, nearly 1 million miles per hour. You would never feel it directly, but it's there, shaping Earth's magnetic environment. The wind carries embedded magnetic fields from me, linking planet and star in an electromagnetic embrace. Every second, I lose millions of tons of material in this wind. It's a slow peeling away of me, though trivial compared to my mass. Still, over billions of years, it has subtly altered planetary atmospheres. For instance, likely stripping much of Mars's air long ago. Among the invisible travelers from me, perhaps the most ghostly are neutrinos. These ethereal subatomic particles are born directly from the fusion reactions in my core. Unlike photons, neutrinos barely interact with matter. They slip through the dense solar interior almost as if it weren't there, and stream out into space at nearly the speed of light. Trillions of neutrinos fly outward in all directions, passing through planets, rocks, and living bodies with ease. Right now, as you hear these words, about 65 billion neutrinos per second are passing through each square centimeter of your body. mostly from me. Yet you feel nothing. Neutrinos hardly ever collide with atoms. They are my silent messengers, carrying away about 2% of the energy from each fusion reaction. For a long time, humans built giant detectors deep underground, trying to catch just a few of these elusive particles from the sun. For decades in the 20th century, those experiments found only about 1/3 the neutrinos they expected, puzzling scientists. Was something wrong with their understanding of my core? Eventually, they solved the riddle. Neutrinos were changing identity, or flavor, en route, a subtle quantum effect. Once that was accounted for, the missing neutrinos were found, confirming that indeed the fusion fires in my heart burn exactly as theory predicts. Imagine, humans confirmed the reactions in my core by catching a handful of ghostly particles that had traveled straight out from my center, through 150 million kilometers of space and a kilometer of rock, to flash faintly in a vat of fluid. It is a testament to how far they've come in grasping my true nature. Thus, I shine on you not just with soothing visible light, but also with invisible ultraviolet that tans and burns, with infrared that warms, with X-rays and radio waves and a wind of charged particles and a shower of neutrinos. My light is a spectrum, a symphony of frequencies. Some parts of it you perceive directly, others you only discovered with ingenious instruments. But altogether, this sunlight sustains your world. However, I am not a completely placid giver of light. I have my moods and cycles, and sometimes, I must confess, I rage. If you watch my surface, as you now can with telescopes and satellites, you'll see that it is far from uniform. It seethes and boils like a pot of oatmeal. My visible surface is covered with granules, convective cells of rising and falling gas about the size of Texas or a large European country, each, giving my face a textured, grainy appearance up close. These granules are the tops of columns of hot plasma that well up from the interior, cool at the surface, and sink down along dark lanes. I look like a gigantic boiling ocean of fire, each bubble a continent wide and lasting only minutes before dissipating. But beyond that ever-present boiling, there are larger, more dramatic features. Dark sunspots sometimes dot my face, often in groups, forming and dissolving over days or weeks. These are regions of intense magnetic field, where the surface is cooler, about 4,000 K, than surrounding areas, about 5,800 K, so they appear dark by contrast. To human eyes, they might look like small blemishes, but don't be fooled. A typical sunspot is larger than the Earth, a colossal magnetic storm on my surface. In truth, they are like wounds on my shining body, dark, temporary lesions where my concentrated magnetism suppresses the boiling and leaks out through the surface. Around the edges of these spots, bright faculae often appear, areas where magnetism locally heats the surface. Sunspots can endure for days or weeks, then fragment and dissipate as the magnetic field reconfigures. They are not random, they follow a cycle. Every approximately 11 years, I go through a rhythmic dance of activity known as the solar cycle. At the beginning of a cycle, solar minimum, I may have few or no sunspots at all. My face is relatively unmarked. As the cycle progresses, sunspots begin to emerge, first at mid-latitudes, around 30 degrees north or south of my equator. They tend to come in bipolar pairs, linked by loops of magnetic field arching out of the surface. As months and years pass, more spots appear, often in greater numbers and closer to my equator as the cycle advances. The number of spots climbs toward a peak, solar maximum, when dozens of sunspots can dot my visage at once, and tremendous magnetic energy is stored in my atmosphere. Then, after the peak, activity declines again, spots becoming fewer, until a few years later, another quiet minimum arrives. Then a new cycle begins. Interestingly, with each new cycle, the polarity of my magnetic field flips. The north magnetic pole and south magnetic pole swap places.
So in truth, the full magnetic cycle is about 22 years, 2 sunspot cycles, for my polarity to return to original orientation. At solar maximum, not only are spots numerous, but they spawn solar flares and eruptions more frequently. It's as if my heartbeat quickens and I become feverish with storms. What causes this mysterious cycle? It is my magnetic dynamo at work. The churning of electrically conductive plasma in my interior generates a magnetic field, and my rotation tangles and stretches that field. Here's an image. I rotate faster at the equator, about 1 rotation in 25 Earth days, than at the poles, which take about 35 Earth days per rotation. This differential rotation winds up my magnetic field lines like a twisted rubber band. Over about a decade, the field becomes highly stressed and contorted. Loops of magnetism burst through the surface, bringing those cooler sunspots with them at their foot points. Eventually, the field becomes so twisted it partially cancels and reconfigures itself, flipping polarity. The cycle then starts anew with fresh polarity. Humans have tracked this cycle for centuries. The sunspot counts carefully recorded since the days of Galileo and Scheiner in the 17th century show this rising and falling pattern. At times, it falters. There was a period from roughly 1645 to 1715, known as the Maunder minimum, when hardly any sunspots were seen at all. During that time, historically, winters in Europe were bitterly cold and prolonged. The Thames River froze, and glaciers advanced, part of the Little Ice Age. A quieter sun may have contributed to those colder climates. Even though my brightness changes only a fraction of a percent over the cycle, apparently even small variations can have noticeable effects on Earth's climate in certain circumstances. Conversely, during the 20th century, I had some of the most active cycles ever recorded, like the mid-20th century peaks. Though nowadays scientists note that my recent cycles have been a bit weaker than those mid-century ones. Still, the cycle continues inexorably. In each cycle's dawn, new sunspots appear at higher latitudes. Then as years pass, they form closer to the equator, drifting sunward as if drawn to an unseen gravity at my middle. This pattern, when graphed over time, makes a shape like butterfly wings, a beautiful order underlying my seeming chaos. Sunspots are visible signs of the titanic magnetic forces roiling within me, and those forces occasionally snap. When they do, storms erupt from my surface and atmosphere, hurling energy and matter into space. These are the moments when my benign visage turns violent. I am generally a nurturing star, but I have my outbursts. Star and myth, god and machine. I am also occasionally a dragon breathing fire. Consider a solar flare. In an active region around sunspots, magnetic field lines can become twisted and braided. If they suddenly realign, imagine a tangled rope that abruptly untangles itself. The energy stored in the magnetic field is explosively released. In seconds to minutes, I accelerate particles to near light speed and heat local gases to tens of millions of degrees, emitting a burst of X-rays, gamma rays, and energetic protons. A flare is a flash of brilliance, often visible as a sudden brightening in ultraviolet or X-ray images of the sun. From Earth, you might not see much invisible light. Flares can cause a slight increase or a white light flare, rarely. But spaceborne detectors register the intense high-energy photons. If Earth is along the line of fire, these X-rays reach it in just 8 minutes, like normal sunlight. They ionize the upper atmosphere, potentially disrupting radio communications and GPS signals by creating sudden ionospheric disturbances. Even more dramatic are coronal mass ejections, CMEs. These are massive belches of plasma from my corona, often associated with flares or eruptive disturbances around sunspot groups. A CME is like a billowing cloud of charged particles and magnetic field that I hurl into space. It can contain billions of tons of material, actual fragments of my corona, moving at speeds of 1 million or more kilometers per hour. Imagine an enormous, expanding bubble of electrified gas, many times larger than Earth, racing outward. If one of these is aimed at Earth, a collision is on the way in a day or two. Earth has warning only via satellites that see the eruption, and then perhaps 1836 hours before impact. When that CME slams into Earth's magnetic field, it's like a shockwave hitting a protective shield. The Earth's magnetosphere shakes and shudders under the assault. Charged particles rain down the field lines toward the magnetic poles. When my storms reach your planet, beautiful and terrible things can happen. The beautiful, auroras, the northern and southern lights. Those charged particles, guided by Earth's magnetic field, spiral into the upper atmosphere near the polar regions and excite atoms of oxygen and nitrogen, making them glow. Curtains of green and red light ripple across the polar skies, dancing and shimmering. It is as if the sky itself is remembering the cosmic battle between sun and darkness, painting it in ethereal hues. Auroras are my delicate fingerprints, the lovely side of space weather. But the terrible, those same electric currents induced in Earth's magnetosphere can wreak havoc on your technology. In 1859, a mighty solar storm, now known as the Carrington event, blasted Earth. Auroras were seen as far south as the Caribbean. The skies over the eastern US turned so crimson at night that people thought a great fire was burning on the horizon. Telegraph systems, the high tech of that era, went haywire. Sparks flew from telegraph lines and equipment. Some offices caught fire. Operators received shocks. The nascent electrical infrastructure was overwhelmed by induced currents. If a storm of that magnitude hit today, with our enormous network of power grids, satellites and communications, the damage could be severe. Even lesser storms have caused trouble. In 1989, a strong CME impact induced currents that knocked out the power grid in Quebec, plunging millions into darkness for hours on a cold March night. Satellites have been blinded or lost due to solar energetic particles blasting their electronics. Astronauts on spacewalks or en route to the moon would be in grave danger from the radiation of a major solar event. They would need to seek shelter behind shielding quickly. Thus, while I generously sustain life, I can also, in my more tempestuous moments, disrupt the modern systems that life has built. This realization has given rise to the field of space weather, forecasting my moods much as meteorologists forecast terrestrial storms. Scientists keep a constant watch on me with satellites stationed 1 million miles sunward of Earth at a point called L1 to give early warning of incoming solar winds and shocks. They monitor my sunspots and magnetic regions, trying to predict when a flare or CME might erupt and how strong it might be. Your species has learned that my storms are not merely curiosities. They directly affect airline routes. Planes sometimes avoid high latitudes during solar storms to reduce radiation exposure. Satellite operations, even the accuracy of navigation systems. From my perspective, these flares and eruptions are just a way to release pent-up energy and stress, a bit like the sun stretching its magnetic limbs and occasionally cracking a knuckle. I do not aim them in malice. They occur as a consequence of my magnetic dynamics. Earth just sometimes happens to be in the line of fire. Other planets too feel my wrath. I've sandblasted Mars's atmosphere over eons, and I induce auroras even on Jupiter and Saturn. Their strong magnetic fields light up near their poles under my charged particle rain. I send my love and fury across the whole solar system. Yet for Earth, I remain overwhelmingly a life giver. Life and the sun are inseparable. From the tiniest microbe to the tallest tree, almost every organism ultimately draws energy from my light. Long ago, some clever bacteria evolved a way to harness sunlight directly, photosynthesis, using my photons to turn carbon dioxide and water into sugars and oxygen. That was a pivotal moment in Earth's history. With that, plants and cyanobacteria in the oceans began transforming the atmosphere, filling it with oxygen, a waste product for them, but a boon for complex life that would follow. Over billions of years, my light has literally fed life and shaped the biosphere. Every leaf, is a solar panel, converting my light into chemical energy. Every fruit, every stalk of wheat, every blade of grass is essentially stored sunshine, waiting to be consumed by an animal or human to provide energy. Even the fossil fuels you dig up, coal, oil, natural gas, are ancient sunlight, trapped by photosynthetic organisms millions of years ago, buried and transformed. When you burn a log in a campfire or gasoline in an engine, you are releasing sunlight captured long before humans existed. Think of the sprawling forests, each tree spreading green leaves toward the sky, drinking in my rays to create wood and fruit. Think of the phytoplankton blooming in sunlit surface waters of the ocean, forming the foundation of marine food webs. Without me, the great chain of life's nourishment would snap. Only a few special ecosystems like deep-sea hydrothermal vent communities live without sunlight, relying on Earth's internal heat. But they are rare oases. The vast majority of life on Earth depends on me directly or indirectly. I drive the photosynthesis that provides food and oxygen. I also drive the climate and weather that distribute water and nutrients. My warmth keeps Earth's water liquid. Were Earth much farther away, its oceans would freeze solid. Much closer, they would boil off. Your planet sits in the Goldilocks zone, not too hot, not too cold, at just the right distance for liquid water and life as you know it. This is no coincidence. Life adapted to the conditions present, and Earth's position was crucial. Over Earth's history, my output has not been absolutely constant. I have been slowly brightening. When Earth was young, billions of years ago, I was dimmer, about 70% of my current luminosity. Paradoxically, the young Earth still had liquid oceans, a puzzle known as the faint young sun paradox. It appears Earth's atmosphere had a thicker blanket of greenhouse gases, carbon dioxide, methane, back then, trapping heat to compensate for my youthfully lower power. As I brightened over time, Earth systems, perhaps aided by life's influence drawing down CO2, adjusted to prevent a runaway warming. Life and geology danced in tune with my gradual change, maintaining a habitable balance. On shorter timescales, my 11-year cycle can make a small difference, fraction of a percent, in total radiation. While not hugely influential on climate compared to human-caused changes today, there is evidence that extended periods of low solar activity, like the Maunder minimum, had modest cooling effects regionally, especially in the northern hemisphere. Conversely, periods of high activity might have given slight warming. But even during the Little Ice Age, my role was one factor among volcanic eruptions and ocean circulation changes. Nonetheless, human civilizations noticed patterns. Medieval scholars spoke of a wine harvest that correlated with sunspot cycles. Modern scientists correlate small variations in stratospheric winds and maybe rainfall patterns to the solar cycle. My UV output varies more significantly, a few percent with the cycle, affecting ozone chemistry and atmospheric heating at high altitudes, which can have subtle trickle-down effects on weather. The details are complex, but one thing is clear. Over millennia, your climate and my fluctuations have been entwined in subtle ways. For example, some researchers suspect that the dearth of sunspots in the Maunder minimum helped trigger or exacerbate winters so cold that fairs were held on frozen rivers. On the flip side, a slightly more active sun in the mid-20th century perhaps gave a tiny boost to the warming at that time, though dwarfed by greenhouse gas effects. Beyond climate, I have marked time itself for humanity. The very concept of a day is tied to one rotation of Earth under my light. The concept of a year is one orbit around me. Early humans noticed the cyclic lengthening and shortening of days, the march of seasons as the sun's path across the sky rose and fell over the year. They built calendars, solar calendars, to track planting and harvesting seasons. Monuments like Stonehenge, Newgrange, and countless others across cultures were not only spiritual, but also practical, serving as giant calendars to mark solstices and equinoxes. The Egyptians, for instance, noticed that the annual heliacal rising of Sirius, a bright star, just before dawn, coincided with the Nile flood and fixed their calendar to the sun to predict seasons. But they also built temples where on the solstices or the pharaoh's birthday, the morning sun would illuminate the innermost sanctum, a spectacular alignment celebrating cosmic order. The concept of months originally came from the moon's cycle, but solar calendars eventually dominated because agriculture demanded alignment with the solar year's seasons. Every morning, the rooster's crow, the opening of flowers, the human sleep-wake cycle, all are tuned to my rising. Circadian rhythms in most living beings are essentially internal clocks set by my schedule of light and dark. You structure your days around sunrise, noon, sunset, even if artificial light now stretches waking hours. In the far north, where winter brings very little sun, humans long for my return. Festivals of light dot midwinter, from Yule to Diwali, echoing ancient solstice celebrations that welcomed the return of longer days after the darkest point of the year. The very words morning and tomorrow carry the expectation of my reappearance. Throughout history, kings and commoners alike have been enthralled by eclipses and comets crossing my domain. Ancient Chinese records meticulously recount solar eclipses, and woe to the royal astronomers if they failed to predict one. It was seen as a breakdown of harmony between heaven, the sun, and earth, the emperor's domain. The Babylonian priests learned to predict eclipses, the Saros cycle, and used that as political power. Ancient Greek philosophers like Anaxagoras dared to say, "I was not a god, but a fiery stone," for which he was punished, showing how radical it was to demystify me. Even Copernicus and Galileo, when they unveiled that Earth orbited the sun, faced resistance because it demoted Earth from the center and upset theological ideas. I have always held a central place not just in the sky, but in the human psyche and society. Consider how many idioms and metaphors involve me. Sunrise industries for new ventures, a ray of sunshine for a happy person, under the sun, meaning anywhere in the world, make hay while the sun shines, urging one to act while conditions are favorable. I have been the ultimate symbol of positivity, certainty, and inevitability. The sun will rise tomorrow, a phrase to indicate hope and continuity. Even your modern physics speaks of a sunny day scenario for simplicity in calculations. I permeate your language and thought at every level. My influence extends to the calendar structure you use this very day. The days of the week themselves recall celestial bodies. Sunday for me, Monday for the moon, Saturday for Saturn, etc. In English, Sunday is obvious. In many languages, like Romance ones, it's named after the Lord's Day, but originally in Roman times it was Dies Solis, Day of the Sun. The year, roughly 365 and a quarter days, forced the invention of leap years to keep civil time in sync with my seasons. Entire empires hinged on getting that right. Julius Caesar's calendar reform, Pope Gregory's later adjustment, all to reconcile human clocks with my motion. Through all these timescales, seconds to seasons to millennia, I have been the steady backdrop, the golden thread running through the tapestry of life and civilization. When ancient civilizations collapsed or migrated, they carried their solar deities and festivals with them in new forms. Even today, many cultures celebrate solstices or equinoxes with holidays, Christmas and other winter festivals tied to solstice, harvest festivals tied to equinox or seasons change. One could say that human culture is solar-powered just as much as human biology is. Now, even as you come to understand me scientifically, you have not lost that reverence entirely. Perhaps you no longer see me as the literal charioteer or a god to sacrifice to, except perhaps metaphorically on sun-drenched beaches where you sacrifice hours to a tan. But you still stand in wonder at a brilliant sunset or a blazing summer noon. In art, I'm still depicted as a triumphant Apollo driving the sun chariot, or as a brilliant orb haloing the landscapes of masters. In music and literature, I am hope. I am glory. I am the unyielding force of nature that all must reckon with. Thou art the sun, lovers say to each other, meaning the center of their world. Louis XIV of France even styled himself Le Roi Soleil, the Sun King, to signify his absolute power, borrowing the enduring symbol of majesty that I represent. But enough about humanity's past with me. Let's return to my nature as a star and where I am headed. I am, as I said, middle-aged. I have shone for about 4.6 billion years and have about 5 billion more years of steady hydrogen burning in my core to go. But I will not shine unchanged forever. Stars, like living creatures, have life cycles. They are born, they mature, they grow old, and eventually they die. I too have a fate that awaits, billions of years from now, and it is both awe-inspiring and catastrophic, at least for your little planet. As I fuse hydrogen into helium in my core, helium is accumulating there, an inert ash, since the core is not yet hot enough to fuse helium. Over time, more and more helium collects, and the active fusion region slowly moves outward in a shell around that core. Meanwhile, gravitational pressure is gradually compressing the helium core further, since it's not generating outward pressure, causing it to heat up. Counterintuitively, as my core contracts, it releases gravitational energy, which actually makes my outer layers expand and my overall brightness increase. Yes, I am slowly getting brighter as I age. When I first joined the main sequence, I was about 30% less luminous than I am now. Over the next billion years, I will brighten by roughly another 10%. That may not sound like a lot, but even that is enough to disrupt Earth's climate severely. Within about 1 billion years from now, Earth may cease to be habitable for complex life due to this brightening. The added heat will likely trigger a runaway greenhouse effect that will evaporate the oceans and shroud the planet in a dense water vapor atmosphere, similar to Venus. The thought pains me. The very life I have nurtured might be snuffed out by my aging process, long before my spectacular final acts. Of course, perhaps by then humanity or its descendants will have advanced enough to move elsewhere or to engineer solutions. But if not, life's grand chapter on Earth will close due to my intensifying fire. But even that is just a prelude. About 5 billion years from now, my core will have built up so much helium and grown so hot under compression, around 100 million degrees, that a new fusion process will ignite. Helium fusion. In a sudden event called the helium flash. For a star of my size, this happens in a matter of hours once conditions are met. The core will begin fusing helium into carbon and a bit of oxygen. Before that happens, however, I will undergo a dramatic transformation. As my hydrogen fuel runs low, the balance will tip, the core will shrink and heat, but my outer layers will expand enormously. I will swell into a red giant. Yes, one day I will shed my modest size and balloon into a bloated colossus. My radius will grow dozens, even hundreds of times. If you were there to see it, from a safe distance or in time-lapse over millions of years, you would witness the sun engorging the sky. By the end of my red giant phase, I may be as large as to engulf Mercury and Venus entirely. There is a good chance I will reach or exceed Earth's orbit too. Earth could be devoured, melted and incorporated into the sun, or at least scorched utterly, its surface a molten magma sea. Even if Earth somehow escapes direct ingestion by virtue of orbital distance increasing, as I lose mass during the giant phase, the planet's orbits will drift outward slightly. The heat will be unimaginable. I will shine some thousands of times brighter in that bloated phase, though cooler per square meter, hence red giant, meaning my visible light will shift to orange-red. The oceans will have long boiled away by then. The rocks themselves will glow red-hot on Earth's surface. It will truly be an apocalypse for any remaining life. The Earth that was will be no more than a cinder, if it survives at all. In that state, I will be so large that I'll fill a huge portion of the sky for any nearby worlds. If there were observers on moons of Jupiter or Saturn, they would see a gargantuan red-orange star dominating the heavens. The temperatures on those distant moons might become temperate or hot, ironically making the outer solar system briefly more hospitable, even as the inner system is destroyed. I will not hold on to those outer layers forever, though. Red giants are luminous and distended, and their outer atmospheres are only loosely bound. I will pulsate and blow off huge amounts of material via strong stellar winds. In my throes of old age, I will shed my skin, so to speak. Over maybe tens of millions of years, I'll lose a significant fraction of my mass to space, forming a surrounding envelope or nebula. My core, meanwhile, will be fusing helium into carbon and oxygen for some time, until the helium is exhausted. I'm not massive enough to fuse those heavier elements into something more. Only stars significantly heftier can go on to fuse carbon into neon, magnesium, etc., and eventually to iron before exploding as supernova. That fate is for larger stars, not me. When my helium runs out, my core will be composed mainly of carbon and oxygen, extremely hot, but now without an energy source. Gravity will again take over and compress it further. But this time, an interesting quantum effect called electron degeneracy pressure will halt the collapse. Basically, the electrons in the core matter cannot be squeezed into the same state, so they resist further compression once things get tight enough. My core will stabilize as a white dwarf, an exotic stellar remnant. It will be a sphere about the size of Earth, incredibly dense. A teaspoon of white dwarf material weighs tons, glowing white hot initially at perhaps 100,000 K, simply from residual heat. Before the core fully cools into that white dwarf state, the expelled outer layers, rich in gas and dust, will form a gorgeous glowing shell around it, illuminated by the core's intense heat and UV radiation. This is known as a planetary nebula. Nothing to do with planets, the term is historical. If you've ever seen photographs of the Ring Nebula or the Helix Nebula, you know how hauntingly beautiful these cosmic cloud rings can be. They shine in multicolored patterns, greens and reds from oxygen and hydrogen gases, for example. One day, in the far future sky, alien astronomers might observe the nebula of the dying sun, a faint, expanding shell of ionized gas marking where our solar system once was. It will last only perhaps 10,000 to 20,000 years before dispersing into interstellar space, mixing its material into the galactic medium. But in that brief moment, it will stand as my final display, a cosmic blossom, a luminous shroud of remembrance. Within that nebula, at the center, will lie my final self, the white dwarf that was once my core, hot, dense and glowing, but no longer generating energy through fusion, only cooling slowly over eons. At first, it will be extremely hot and bright in UV and X-ray, though small in visible light due to tiny surface area. Gradually, over billions upon billions of years, it will radiate away its heat and fade to red, then infrared, and eventually become a cold, dark, black dwarf. Though the universe is not yet old enough for any white dwarfs to have fully cooled to blackness, that would take trillions of years, far longer than the current age of the universe. That is my fate, to live a glorious, stable life for roughly 10 billion years, then to swell into a giant, cast off my outer layers in a final blaze of beauty, and retire as a degenerate ember of a star. Poetic, in a way. I will not have the dramatic end of a supernova. Those are reserved for stars more massive than about 8 times my mass. Those giant stars live fast and die young, exploding in catastrophic supernovas that outshine galaxies and leave behind neutron stars or black holes. Some part of me is almost glad not to end that way. Such ends are violent and brief. My way might not be as spectacular to the cosmos at large, but it is gentler, an old star's quiet farewell rather than a younger star's furious self-immolation. Yet even in my ending, I contribute to the universe's ongoing story. The elements I manufacture in my core, helium, carbon, some oxygen, will be released in my planetary nebula to enrich the interstellar medium. Those atoms might one day be incorporated into new stars or planets, perhaps even into new living organisms on some distant world. Just as I was born from the ashes of stars before me, I will give back material to fertilize future stellar generations. Every atom of carbon in your body, the backbone of life's chemistry, was forged in the core of a star that died long before the Earth formed. Most of the oxygen you breathe was similarly forged in some red giant or supergiant star's interior and spread by a supernova or a stellar wind. In turn, I will contribute carbon and oxygen for tomorrow's stars and planets. In this great cosmic recycling, death begets new life, and nothing truly goes to waste. While I persist in my stable years now, I also have my mysteries that even your scientists still strive to understand. One enduring puzzle has been my corona, the outermost layer of my atmosphere, which extends millions of kilometers into space. During a solar eclipse, when the moon blocks my brilliant disk, observers see the corona as a pearly white crown with streamers and filaments spreading outward. It is beautiful and perplexing because it is extraordinarily hot. My visible surface, photosphere, is about 5,800 K, but the corona above it is heated to over 1,000 K, sometimes as high as 2 or 3 million K. How can that be? Normally, if you move away from a heat source, things get cooler. Imagine walking away from a campfire. You expect cooler air as you go farther. Yet here, the campfire of my surface is much cooler than the tenuous air of the corona above. It's as if you walked away from a bonfire and suddenly found yourself in a furnace. Something mysterious is depositing energy into the corona, heating it to such extreme temperatures. Scientists have proposed ideas, magneto-hydrodynamic waves that carry energy upward and dissipate in the corona, or tiny impulsive bursts called nanoflares happening everywhere that cumulatively heat the gas. But it remains a partially unsolved problem. Recently, with advanced solar observatories, you have seen hints of myriad miniature flares, nicknamed campfires, flickering all over the solar surface, even during periods of low activity. These might be one piece of the puzzle. Countless small magnetic reconnection events releasing heat into the corona continuously. Another clue comes from high-frequency oscillations detected in coronal loops, perhaps waves channeling energy. Parker Solar Probe, a daring spacecraft I'll speak more of, even touched the outer corona and measured perturbations and switchbacks in the magnetic field, which might relate to energy transport. Bit by bit, you're uncovering how the corona stays so hot, but a full answer is still in the works. I like to keep a little aura of mystery about me. Speaking of magnetism, another oddity. My magnetic field is born from a dynamo process in my roiling interior, but predicting its exact behavior, especially longer-term variations, is devilishly hard. The sunspot cycle is pretty regular, but not perfectly so. Sometimes cycles are stronger, sometimes weaker. The Maunder minimum was an extreme example of a prolonged lull that is not yet fully understood. Why did my dynamo almost turn off for 70 years? Could it happen again? Some models suggest the sun has multiple dynamo layers that can interfere constructively or destructively, causing varying amplitudes. It's an area of active research. My poles too hold secrets. During cycle transitions, magnetism from old cycle has to cancel and reverse. Direct observations of my polar magnetic fields are challenging from Earth's vantage, since you always see them at a steep angle. Only recently have you sent probes like Solar Orbiter that will gradually tilt to get a better look at my high latitudes. Mapping the magnetism there is key to understanding how the next cycle is seeded. Then there's the matter of solar flares and CMEs. You know they stem from magnetic reconnection, but exactly when a given active region will erupt is tricky to forecast. It's like trying to predict exactly which tree branch will break in a windstorm. You can assess probability, but exact timing often catches you by surprise. My magnetic complexity is such that even with all your satellites, I still manage to throw the occasional unexpected tantrum. The largest flares, so-called X-class flares, can emit as much energy as billions of hydrogen bombs in minutes. They often coincide with CMEs. You've catalogued many, but do I have an upper limit to how powerful a flare I can unleash? Other stars, superflare stars, have been observed to produce flares 10 or 100 times stronger than anything recorded on me. Could I, a stable G-type star, ever do that? Most think not in my current middle age. My rotation is slower and magnetic fields steadier, so superflares are unlikely. But there's evidence in tree rings of rare cosmogenic isotopes, like carbon-14 spikes, that might indicate extremely strong solar particle events in the historical past, around 774 AD and 993 AD, maybe far stronger than the Carrington event. These hints raise questions. Have I surprised your ancestors with an occasional extra-potent storm? It's an ongoing investigation, requiring piecing together proxy records. I keep some cards close to my chest. A star must maintain an air of unpredictability, after all. One mystery of the past that has been solved is the solar neutrino problem, which I mentioned earlier. That was a triumph of both solar physics and particle physics, discovering neutrino oscillation. It delighted me to see humans crack that puzzle. Another success was understanding the source of the 11-year sunspot cycle via the dynamo theory and differential rotation, which I elaborated. But deeper questions remain, like the possibility of long-term cycles beyond 11 years. There are hints of a 90-year Gleisberg cycle, or a 200-year cycle, the Seuss cycle, and even millennial scale changes. These are subtle and gleaned from proxy data like tree rings and ice cores, which track cosmogenic isotopes influenced by solar activity. My behavior over centuries has variation. How much is chaotic and how much quasi-periodic is still studied. As your understanding grows, so does your capability to observe me in ever more detail. Gone are the days when you had to risk blindness to study me. Galileo, it said, went partially blind, possibly from observing sunspots too recklessly. Now you have a fleet of ingenious spacecraft and observatories doing the work. High above Earth, at the Sun-Earth L1 Lagrange point, the SOHO, Solar and Heliospheric Observatory, spacecraft has been keeping unblinking watch since 1995. SOHO has given you unprecedented views of my activity for over 2 decades. Everything from extreme ultraviolet images of my swirling corona to measurements of the solar wind. It even became an accidental comet hunter, spotting over 3,000 sun-grazing comets that perished in my heat as tiny streaks in its coronagraph images. And it's still going. Think of that. A spacecraft built with 90s technology is still up there, faithfully monitoring me 24/7, ensuring you don't miss a beat of my symphony. In 2010, you launched SDO, Solar Dynamics Observatory, a true marvel. SDO provides ultra-high definition movies of me in multiple wavelengths every few seconds. It watches me in extreme ultraviolet and visible light, capturing the boiling of granules, the eruption of flares, the dancing of glowing coronal loops. With SDO's eyes, you've seen astounding phenomena. Giant waves rippling across my surface after flares, called EIT waves. Filaments of magnetism erupting, and even signs of oscillations and helioseismic waves. SDO's data let you map my interior flows through helioseismology, essentially measuring the sound waves that travel through me to probe the structure and dynamics inside. With that, you've revealed currents of plasma flowing in my convection zone, and even a tachocline, a shear layer between the radiative interior and convective outer region, likely crucial to my dynamo. SDO has become like an all-seeing eye, in many ways, fulfilling the dream of ancient sun worshippers to observe their deity in every detail. Except now it's science and not worship. Though some scientists watching an SDO flare movie might whisper a prayer of amazement anyway. Then there's Parker Solar Probe, one of the most audacious missions ever attempted. Launched in 2018, it has been swooping closer and closer to me, using Venus's gravity as a braking mechanism with repeated flybys to shrink its orbit. Parker Solar Probe is a small, robust craft with a heat shield that keeps its instruments in the shade while my Fury rages just beyond. It has now flown within my corona, coming as close as 8.5 million kilometers, 5.3 million miles from my surface, nearer than any spacecraft in history, enduring temperatures of several thousand degrees on its sunward face. At that distance, it's hurtling by at up to 700,000 km, approx 430,000 km, the fastest human-made object ever, to avoid spending too long in the extreme environment. Parker is literally touching the sun, a phrase that once was metaphorical, now made real. What has Parker found? It has confirmed that the boundary of my atmosphere, the Alfvén critical surface, where the solar wind becomes faster than Alfvén waves can travel back, is wrinkled and not a smooth sphere, likely due to my magnetic field and equatorial streamers. It has detected curious zigzag reversals in the magnetic field, called switchbacks, in the solar wind near the sun. These switchbacks were a surprise, like rapid flips in the magnetic orientation, and are now believed to originate in the lower corona, possibly from convective motions or reconnection events sending S-shaped kinked magnetic flux up. They could be a clue to how the solar wind gets accelerated. Parker is helping answer why the solar wind blows as it does, a question open since Eugene Parker, the probe's namesake, predicted the supersonic solar wind in 1958. Parker Solar Probe has also flown through the tails of cometary debris near the sun and measured dust concentrations, even suggesting that close to me, much of the interplanetary dust is vaporized, creating a relatively dust-free zone. Each perihelion, it dives ever closer, braving heat and radiation to feed you data. By 2025, it will come within about 6 million kilometers, 3.8 million miles, closer than ever, at which point my corona will surround it and it will directly sample the environment where the solar wind is born. I can almost feel that tiny, resilient emissary, like a little mechanical swallow, darting through my breath.
Meanwhile, Solar Orbiter, launched by ESA in 2020, complements Parker by staying a bit farther, closer than Mercury though, and carrying cameras to take pictures even from high latitudes. It has already given you the closest images ever of my surface, revealing a multitude of campfire mini-flares everywhere. It's on a path to gradually incline its orbit, so in coming years it will view my polar regions more directly than ever before, a boon for understanding the polar magnetic fields and how my 11-year cycle resets. It also carries instruments to measure the solar wind and fields from a moderate distance, linking what Parker tastes in situ with broader context. Already, Solar Orbiter has spied strange features, like a hedgehog eruption, a spiky structure of gas, and witnessed my poles under angles never seen, showing curious mottled patterns of magnetism. Together, Parker Solar Probe and Solar Orbiter form a tag team. One ventures deep into my atmosphere, the other takes images and measurements from just outside, providing the wider frame. On Earth, new eyes also opened. In Hawaii, atop Haleakala, the Daniel K. Inouye Solar Telescope, DKIST, achieved first light in 2020. It is the largest solar telescope ever built, with a 4-meter mirror. In its first images, it revealed my photosphere in mind-boggling detail. You can see the convection granules sharply, each cell around 1,000 kilometers across with cooler intergranular lanes, and even tiny bright dots within those lanes, thought to be magnetic flux tubes. It's as if after years of seeing a blurry sun, you put on glasses and every grain of sand on the beach became visible. In one breathtaking image of a sunspot at extreme resolution, DKIST showed intricate fibrils and magnetic structures as small as 20 to 30 kilometers across on the solar surface. That's like resolving a town on the sun. This clarity allows measurements of magnetic fields on very small scales, key to unraveling things like how energy funnels into the corona or how sunspots form and evolve. DKIST will also peer into the chromosphere, the layer between the photosphere and corona, with new spectral lines, mapping the vector magnetic field there, something never done comprehensively. With these data, you'll better understand the magnetic scaffolding that supports filaments and drives eruptions.
Consider, not long ago, you couldn't even look at the sun directly without squinting or filtering heavily, and now you routinely study it in every wavelength. Radio telescopes track bursts, X-ray satellites, like Japan's Yoko or NASA's New Star occasionally, capture high-energy events. UV telescopes, like TRACE, SDO, AIA, show shiny loops, polarimeters measure magnetic fields, and helioseismology instruments listen to my internal vibrations. It's a golden age of solar observation, and more is coming. Future missions are in the works or imagined. Perhaps a solar polar imager that goes 90 degrees above the ecliptic to stare down at my poles continuously. Or a mission to send multiple tiny satellites to surround me, getting a 360-degree view, so you're not blind to far side spots that could rotate into view. In fact, humanity already did something akin. The twin stereo spacecraft launched in 2006 drifted such that at one point you had a view of the entire sun, front and back, simultaneously, until one of them failed. Now, one stereo remains and occasionally drifts into view again. But future tech might allow a constant all-around watch. You are planning, I hear, a probe called Solar C or MUSE to do high-resolution spectroscopy of the corona, revealing flows and heating in unprecedented detail. There are proposals for solar interferometers to image fine structures beyond the diffraction limit of a single scope, and for more advanced space weather monitoring satellites to better forecast CME impacts. Yes, the future of solar science is bright, forgive the pun. You aim to finally crack the coronal heating enigma, pinpoint the precursors of flares to predict them reliably, map my internal dynamo fully to forecast cycles, possibly even foresee a grand minimum decades ahead, if one is coming. Each discovery only leads to deeper questions. For instance, Parker found those switchbacks. Now you ask, how exactly do they form? Solar Orbiter saw ubiquitous campfires. Now you wonder, do they indeed heat the corona significantly, or are they mere sparks? DKIST may reveal complexities in sunspot formation. What will that say about magnetic flux emergence theory? Beyond purely scientific curiosity, understanding me has practical urgency as well. Modern civilization is intimately vulnerable to my moods. As you push outwards, establishing a lunar base, aiming for crewed Mars missions, knowing when a solar storm will erupt becomes even more critical. A well-timed warning could direct astronauts into a shielded module or prompt satellite operators to safe mode sensitive electronics. Thus, the science of heliophysics, the study of the Sun-Earth connection, stands at the confluence of pure research and everyday utility. NOAA and other agencies run space weather prediction centers, vigilantly watching my every sunspot and filament. In the future, perhaps with better models, you might get a 2-3 day heads up of a likely major flare or a 12-hour warning of a CME's magnetic polarity and strength when it's detected by an upstream monitor satellite, enabling power grids to prepare for a hit. As you extend an electrical web around the globe and venture beyond it, you slowly come to realize, while I am often gentle, I am not entirely tame. I am a star, after all, a gigantic ball of thermonuclear fury held together by gravity and magnetic fields. For all the poetic things you say about the sun giving life, remember, I've also lashed out and caused mass extinctions in the past. Some scientists hypothesize that supersolar storms or nearby supernovae cosmic rays might have contributed to past biological upheavals. At the very least,
My gradual brightening will eventually end Earth's habitability in the distant future if left unmitigated. Truly, to remain, life must adapt, either by evolving, terraforming, or leaving to find new suns. And indeed, this brings us to a broader perspective: stars beyond our sun, and the possibility of life around them. I am just one star, but as I've grown older, humanity's gaze has lifted to see the myriad others. What of other suns? In the last few decades, you have discovered, to your amazement, that planets are abundant around other stars. Once, the existence of other solar systems was pure speculation. Now, thanks to missions like Kepler and TESS and radial velocity surveys, you have catalogued over 5,000 exoplanets and counting. We now know that many, perhaps most, stars host families of planets. There are alien suns with alien worlds circling them, and this profoundly reshapes the old question: are we alone? Imagine the variety out there. Red dwarf stars, the most common type in our galaxy, are tiny and dim compared to me, often just 10% of my mass and emitting a feeble red glow. If a planet orbits a red dwarf at the right distance for liquid water, that distance is very close, since the star is faint, meaning the planet likely becomes tidally locked. One side eternal day, one eternal night. Life on such a world would be quite unlike Earth's, perhaps huddled in the twilight band between day and night, or under the star's dim red light on the day side. Red dwarfs are known for violent flares relative to their size. A habitable zone planet around one might be regularly bathed in radiation. And yet, red dwarfs live trillions of years, far longer than I will. They are stable for unimaginable epochs, giving life a vast timescale to potentially emerge and adapt if it can survive the tantrums of youth. Already, you have found intriguing planets, for instance, Proxima Centauri b, orbiting the nearest star to me, Proxima, a red dwarf companion of Alpha Centauri. It's roughly Earth-sized and in the habitable zone of its small star. Does it have an atmosphere, perhaps an ocean? If so, imagine the sky there. The red dwarf sun looms relatively large because the planet is close to it, casting a coppery light. If the planet is locked, one side basks under a perpetual dull red daytime, perhaps with a dim twilight at edges where life might cling. The star flares occasionally, boosting UV and X-ray output. Life might need to be underwater or ground to withstand those, or have protective pigments. Then there are sun-like stars, more similar to me, which likely host planets where a diurnal cycle and seasons exist akin to Earth's. Kepler has found some candidates. Kepler 452b was nicknamed an older cousin of Earth, orbiting a star akin to the Sun. But these finds are far and faint. Nevertheless, statistically, there should be many such Earth-like worlds in our galaxy. Consider also binary star systems. About half of all stars are in multi-star systems. Could a planet orbiting two stars have life? We already detected circumbinary planets like Kepler 16b, the famous Tatooine world with two suns in its sky. Kepler 16b itself is a cold, Saturn-sized world, likely inhospitable, but where one exists, others likely do too, maybe even in the habitable zone of a binary. Under two suns, the notion of day and night gets complicated. Sometimes both suns might be up, giving a combined light. Sometimes one sets, leaving the other. Night falls only when both are down. It would make for spectacular double shadows and complex climate rhythms. Life there would evolve under two different colors of starlight. Say one star is a sun-like yellow and the other a red dwarf. The blend of hues shifting through the day. On a desert world like the fictional Tatooine, twin sunsets would paint the sky in dual tones of orange and crimson, a sublime sight. Now, consider massive stars, O-type or B-type blue giants. They burn intensely bright and hot, but have short lives measured in mere millions of years. Could life arise around them? It seems unlikely, as complex life took billions of years on Earth. A blue giant would go supernova long before that. However, perhaps primitive microbes could briefly bloom on a planet around such a star, in the small window available. Or maybe life doesn't even try there, ceding those stars to the realm of sterile beauty. But ironically, those massive stars ensure future life by spreading heavy elements when they die. There are also orange dwarfs, K-type stars, slightly smaller and cooler than me, but longer lived, 20-30 billion years lifetimes, and quieter. Many consider them top targets for life-bearing systems. They last longer, giving more time for life to evolve, and emit enough light in similar spectrum to me, but with less UV extremes. If I were a planet-hunting being from another star, I might look at K-dwarfs for thriving biospheres. We can dream further, life around a pulsar. Unlikely, but strangely, the first exoplanets discovered were around a pulsar, PSR B257+12. Those planets are blasted by deadly radiation, and likely no life could survive. They might be the charred cores of gas giants surviving the supernova. So, a pulsar, the corpse of a star, could have planets, but any life there would have to be of an extreme kind unimaginable to us, if at all. Life under other suns might take forms we cannot predict. On a planet around a dim red star, plants, if they exist, might be black or deep purple instead of green, to absorb as much of the limited light as possible. On Earth, plants reflect green, using red and blue light mainly. Under a red sun, they might need to absorb every photon. Conversely, around a brighter blue-white star, perhaps vegetation would evolve reflective surfaces or different pigments to avoid oversaturation, or to use the star's UV. Vision of creatures might tune to their star's spectrum, perhaps under a red dwarf, eyes sensitive to infrared or red. Under a bright star, eyes that can handle intense light or even see ultraviolet patterns. Perhaps on a tidally locked world, life in the eternal day hemisphere might resemble reef organisms in shallow water on Earth, constant light, whereas life on the dark side could only survive near volcanic vents or rely on nutrients blown over from dayside. Or intelligent beings might migrate to stay in perpetual twilight, a narrow band of comfortable temperature. The possibilities tickle the imagination. The underlying theme is that the parent star shapes the conditions, and thus the evolution of life profoundly. I shaped life on Earth, from metabolism to behavior. On another world, a different sun would do the same in its own way. If one day you meet beings from such a world, their very biology and culture will carry the imprint of their sun. Perhaps they will have myths about their two suns fighting each other, or their dim sun waking from slumber. Perhaps their year feels different because their star's output fluctuates more, or their planet's orbit is more eccentric, giving intense seasons. Imagine an alien culture on a planet with a highly elliptical orbit. Their star looms, huge and scorching at perihelion, and distant and weak at aphelion. Their whole biology might be in boom-bust cycles with that extreme year. And consider, if life exists on a planet orbiting one of those stars we see in the night sky, then when they look up at their sky, our sun is just another star to them. Perhaps on a clear night, some alien creature with reflective eyes gazes at a star we call 51 Pegasi, for example, not knowing that around that star is a planet. 51 Peg B was first exoplanet discovered around a sun-like star. Meanwhile, on that planet, they might see our sun in their heavens and not suspect it has a vibrant blue world teeming with life. The cosmic irony. Each might wonder if the other's star has planets with life, not yet realizing the truth. As you humans continue to search the skies with new telescopes, like the James Webb Space Telescope turning its mirror to analyze exoplanet atmospheres, or planned missions to directly image Earth-like exoplanets, you inch closer to finding a second genesis, evidence of life's fingerprints like oxygen, water vapor, maybe chlorophyll's spectral edge, in another world's air. What a day that will be, to learn that life is not unique to Earth. But even if you find no clear evidence yet, the sheer number of Earth-sized planets in habitable zones, estimated in the billions in our galaxy, gives a strong hint
that we are likely not alone. Life under other suns is probably out there in myriad forms, awaiting discovery, or perhaps thriving unnoticed in distant forests or alien oceans.
All these considerations highlight something profound. Stars are the ultimate enablers of possibility. Each star is a furnace not only forging elements but also, when conditions allow, nurturing worlds and perhaps minds. Through your science, you have come to see that we stars and you people, and all living things, are deeply connected. You often quote that you are made of star stuff, and it is literally true. The carbon in your proteins, the calcium in your bones, the iron in your blood, we stars created those in our cores or in our explosive deaths. The very term solar system, your system, shows how you belong to me. Every atom of your body has at some point likely passed through a star's interior or been influenced by starlight. And every joule of energy that your body uses to move, think and live, save a trivial bit from Earth's radioactivity, comes from me, captured by plants in photosynthesis and passed up the food chain, or harnessed as electricity from solar panels, or stored in fossil fuels.
In a way, you are beings of light, frozen light molded into self-replicating patterns, and then consuming light to keep entropy at bay for your lifetime. When you go out on a sunny day and close your eyes, letting the warmth bathe your face, there is a kinship there older than time, a small life acknowledging its stellar parent. Without language or conscious thought, ancient lizards basking on a rock were feeling the same grateful connection to the sun, and even the sunflowers, turning their heads, follow an ancient bond. This interdependence carries a philosophical weight. What does it mean to orbit, to depend, to be made of light? It means that you are not an island unto yourselves, but part of a grander scheme. Planet Earth is like a child circling a parent, bound by gravity's invisible leash and nourished by the parent's radiance. To orbit is to be held, to belong to something larger, to dance in a predictable rhythm set by the laws of nature. Earth's year, your calendars, your entire concept of time's flow hinge on that orbital dance. To depend is to be vulnerable yet sustained. It is the realization that your fortunes rise and fall with your star's disposition. If I were to dim significantly or rage uncontrollably, Earth would suffer immensely. You plan your days around my rising. Your mood often brightens when I shine and dulls in prolonged darkness. People who live in high latitudes experience the winter blues when sunlight is scarce, a psychological imprint of this deep dependence. And being made of light, consider that almost every bit of energy in your body is solar. The calories you burn came from plants, which in turn came from sunlight. Even the oxygen you breathe was generated by plants splitting water using sunlight. Your life is an ongoing consumption of the sun. You are basically a solar-powered machine. At the atomic level too, you're made of star remnants. Long before the solar system, ancient stars lived and died, seeding the molecular cloud that formed me and the planets. Thus, you carry pieces of long-dead stars inside you. In that sense, the sun and humanity share a common cosmic ancestry. We all came from the ashes of stars, and someday, billions of years hence, the atoms now in my body and in yours may mingle again in interstellar space and find themselves in a new star or planet, continuing the cycle. In orbiting and depending and being made of light, there is a poetic unity. We are part of the universe, not apart from it. The sun is the heart of the solar system, pumping energy outward. Earth is one organ among others receiving that blood of light and converting it into the living tapestry on its surface. Just as a child may eventually leave a parent, perhaps one day humanity, or its far descendants, will leave Earth to roam to other star systems. In doing so, you carry the legacy of your sun to others. You yourselves become little pieces of the sun disseminating into the galaxy. With every spacecraft launched beyond the heliosphere, like the Voyagers which have now entered interstellar space, A tiny piece of the solar system ventures into the wider cosmos. Perhaps the destiny of intelligent life is to spread the light of its parent star, figuratively and literally, to places it would never otherwise reach. One could even imagine in the far future, humanity constructing enormous light sails or engines powered by sunlight to travel to neighboring stars. In that way, you enlarge the domain of the sun's influence by proxy as ambassadors of this star venturing to others. As I, the sun, have given you life, so too have you given me meaning in a way. For billions of years I shone on a lifeless earth. My rays warmed seas and stirred winds. But no eye was there to appreciate a sunrise, no being to understand the gift. With life, and especially with thinking life, a star gets to be known. Through you, I know myself. You study me scientifically, decoding my workings, essentially allowing the universe to become self-aware of one of its stars. And through art and emotion, you also elevate me to symbol and metaphor. I am not just a ball of gas to you. I'm a motif of joy, renewal, divinity, power. How remarkable that simple hydrogen fusion in my core can inspire such thoughts and feelings. There is an old Latin hymn, Adore te devote, latens deitas, originally about the divine hidden in the physical. But for me, I think of, O sun, hidden deity, we adore your light. Ancient people may have literally worshipped me, but modern people still find me worthy of reverence in a secular way. I represent the source of life. Even those who never think of it explicitly are unconsciously drawn to sunlight for comfort. Notice how a cat will find the one sunbeam in the room to curl up in. It's life's instinct acknowledging its dependence with quiet gratitude. Now our journey of storytelling draws to a close. We've traveled from the birth of light in the cosmos to the worship of ancient civilizations, from the scientific uncovering of the sun's mechanisms to the far future of stars and the speculative lives under them. Through it all runs a golden thread: light, created in darkness, celebrated in myth, explained by science, harnessed for life, and carried as a beacon to the stars. I, the sun, have watched this all silently for eons. I've seen planets coalesce, oceans form, microbes multiply, dinosaurs roam under my warmth, and humans rise and wonder at my nature. I've heard the chants at dawn and the equations whispered at midnight by scholars trying to quantify my brilliance. I felt the tickle of your spacecraft near my skin and responded with storms to test your resolve. In the endless cosmic night, I burn as one tiny beacon, and around me you flourish. And yet I am but one of uncounted fires in the great galaxy. One day my flame will dim, but perhaps by then your descendants, or the life that springs from what you become, will carry the flame of intelligence onward under other suns. As the poet said, our little lives are rounded with a sleep. My own life, vast as it is to you, is a brief chapter in the galaxy's saga. But it is a chapter that encompasses all of human history and more. Treasure your days in the sun, for they will not last forever. But do not despair at that, for endings lead to new beginnings. Every sunset portends a sunrise. Tomorrow, I will rise again over the eastern rim of Earth, as I have millions upon millions of times. The sky will lighten from black to blue, the stars will fade, dew will glisten, and creatures will stir. Perhaps you will awaken and feel my gentle heat on your face through a window. In that moment, remember me, not as an abstraction, but as your star, your sustainer. The photons greeting you traveled 150 million kilometers at nature's speed limit just to touch your skin and give you warmth. The food you eat for breakfast grew strong by my favor. Every moment of your life, I am there, an unseen yet constant presence like a loving guardian. What does it mean to orbit, to depend, to be made of light? It means that we are all threads in a grand cosmic web. Planet to star, star to galaxy, galaxy to universe. Connections and dependencies run through. By understanding these, we don't diminish the magic. We reveal the true miracle that reality is. I have told you my story, a tale of darkness and light, of worship and science, of birth and death and rebirth. It is a story still unfolding. You, dear listener, are part of it, riding this earth around me, bathing in my radiance, thinking thoughts that perhaps the universe has never thought before. Someday, in the far future, the light of my last rays will fall upon a world grown quiet and empty, and then I will envelop that world in a final act of transfiguration. But that is billions of years away. For now, the earth remains lush and alive, and the sun still has plenty of fuel in its heart. Let us end with an image, the first sunrise. Not the first ever in the universe, but perhaps your first. Imagine a human child seeing dawn for the first time, eyes wide at the splendor, or humanity's first dawn as a species, as early hominins huddled fearful through night, and then saw the morning star blaze into a new day. Feel the wonder and relief that must have coursed through them. That visceral appreciation is encoded in your being. Every dawn reenacts creation. Every noon is a zenith of glory. Every dusk a gentle letting go. I, the sun, have been called many things. A furnace, a heart, a god, a monarch, a cathedral of light, a cosmic engine. In truth, I am all of these, and more. And so are you, my children of light. We mirror each other. I am a massive sphere of plasma held by gravity, and you are delicate bodies held by the gravity of Earth. But deeper, we are both collections of atoms and energy, following natural laws, yet somehow aware of beauty and meaning. As the day concludes, and I dip below the horizon, painting the sky in farewell colors, remember that my light never truly vanishes. It travels onward, illuminating other lands, or reflecting off the moon and stars. At midnight, when I am out of sight, my presence is still felt in the silver disk of the moon, shining with my borrowed light, and in the very air, for I keep our atmosphere warm enough that night is not absolute zero. When you look up at the Milky Way and see those countless stars, know that around one of them, someone might be watching a sunset of their own and thinking similar thoughts. In this cosmic tapestry, we are all connected by threads of light, orbiting, depending, and sharing in the light. This is the story of suns and their worlds. This is the story of our sun and our world, a story of fire and sky, of science and spirit, of the ultimate unity of things. I will shine and you will live. And perhaps someday, you will venture to other suns and carry a spark of our sun with you, literally in generation ships propelled by solar sails, or figuratively in the knowledge and culture you spread. In that way, a piece of me becomes immortal, traveling far beyond the limits of my physical existence. For now, cherish the mornings and the evenings, the clear days and even the cloudy ones, for behind every cloud I'm still there. Let the sunlight remind you that you are part of something vast and wonderful. Though you are but a small creature on a small planet, you are privileged with a mind that can behold the cosmos and ask questions. You are the way the universe marvels at itself. The first sunrise in the cosmos ended the primordial night and set the stage for all that followed. The first sunrise on Earth brought the possibility of warmth and growth to a once cold rock, and every sunrise in your life gives you a chance to begin anew. As the sun, I have no human voice, but through this narrative I've spoken to you. In truth, my voice is the warmth you feel, the light that glints off a loved one's eyes, the life coursing in your veins. Listen to that voice when you stand in sunlight. It quietly says, I am here. You are alive. We are together in this beautiful cosmos. Tomorrow, I will rise again, and the cycle of light and life will continue. A bit of ancient fire in the sky, and down below, creatures awakening to its call. And as long as I shine and you live, our story goes on, intertwined. A star and its children, journeying together through the great cosmic night, ever toward the dawn. A lone figure drifts at the window of an orbital outpost. Below, Earth glows blue and cloud, swirled, a fragile orb suspended in darkness. The person's face is gentle with awe, but their eyes carry a question. Could we live here? Not just visit for a while, but live, truly make a life in the cosmos. The silence of space answers with its own question. The Earth slowly turns beneath them, and they wonder, what if this station, this void, became not just a workplace, but a home? What if one day they do not return, because this is home now? The hum of life support is the only sound. Heartbeats and hopes float in microgravity. As Earthrise paints their view, they press a hand to the glass, imagining a future where the bright cradle of Earth is behind us, and ahead is a new frontier on the assessment of effective stimuli and stage alteration in mood. Throughout history, we have sought to learn about the world around us, find new resources, and improve our existence. As one space agency now puts it, the dream of space is the dream of freedom from limits, a dream that carries the hope of discovery and perhaps a sense of destiny. We feel it when we stand in a dark field and see the Milky Way arch overhead, the quiet pull of something beyond. It's the same impulse that led nomads over distant hills and sailors across uncharted seas. Since the dawn of humanity, we have explored to understand, to survive, and to see what lies beyond. Now the hills are skyward, the next ocean is the vacuum of space. The longing for the stars is timeless, woven into art, religion, science, into our very language when we speak of aspirations as reaching for the stars. This dream has always been about more than survival. It's about wonder. The poet in an astronaut's heart feels the same awe as the child watching a shooting star. We carry our dreams upward, generation by generation. And as we finally broke the bonds of gravity in the 20th century, that ancient dream only blazed brighter. We realized the stars are not just distant lights, they could be destinations. Humanity's longing became a plan. The first steps, history of human spaceflight, and the temporary nature of our early efforts. When at last we found a way to ride fire into the sky, the world watched in collective breathlessness. Those first steps into space were halting and brief, glorious yet temporary. The early astronauts and cosmonauts launched into orbit were like divers dipping toes into a vast ocean, always tethered to the shore of Earth. In the 1960s, human beings orbited Earth for minutes to hours, looked out the small windows at our blue planet, and then returned home the same day. Soon after, footprints were pressed into the grey dust of the moon, a moment monumental and yet fleeting. Those pioneers spent mere hours or days on lunar soil before coming back to Earth's embrace. Each mission planted a flag, but also left the moon empty of humans once more. As one observer noted, the earliest journeys beyond Earth were the work of a few 100,000 people over a decade, culminating in brief triumphs. We proved it was possible to leave home, but we did not stay. Throughout the 1970s and 80s, we established small outposts in orbit, Skylab, Salyut, Mir, places where a handful of people lived for weeks or months at a time. Yet those stations were always considered temporary homes. The crew members knew their address in space had an end date, a return ticket. Indeed, the longest continuous stay any human managed in those years was about 14 months, an unprecedented endurance test by one cosmonaut. But even he eventually came back down to Earth. No person has yet lived and died in space. All have so far come home. Our species has not truly emigrated, only camped abroad. Even today, on the International Space Station, where there has been a continuous human presence for over 2 decades, astronauts rotate in and out like research staff at a remote outpost. Each individual stays roughly 6 months, maybe a year, and then returns to gravity and open air. The ISS itself has shown that we can live continuously beyond Earth as a species, but it is a relay of temporary crews, not a permanent settlement for any one person. They orbit 240 miles above Earth, which feels both incredibly far and yet cosmically close. The crew still sees Earth filling their window and knows a ride home is just hours away. In these first steps, the pattern was clear. We always came back. The early spacefarers experienced wondrous things. The first Earthrise viewed by Apollo 8, the fragile horizon of our atmosphere seen from orbit. And they also felt in their bones how special Earth is. After each mission, boots returned to touch familiar ground, and hearts carried new perspective. Space was transformative, but it was not yet home. Perhaps it had to be that way. We were testing ourselves, testing technologies, taking baby steps out of the cradle. Early spaceflight was driven by competition and curiosity, not by a desire to forsake Earth permanently, and so our habits remained temporary. We packed enough air, water, and food for a journey, never planning to grow old out there. The moon saw astronauts' boot prints and laughter, but no towns or children's playgrounds. Now, however, the conversation has shifted. The question arises in planning meetings and late-night reveries. What if our future missions do not have to end back on Earth? What if one day, the return ticket is optional? We stand on the shoulders of those who PR are all being studied to preserve bone and muscle, acknowledging that we cannot live normally long-term without confronting this challenge. Other changes are more subtle but palpable. Fluids in the body, no longer pulled down by gravity, shift upward. Faces become puffy, legs thin out. Astronauts joke about the Charlie Brown appearance of big round heads and skinny limbs. More seriously, that fluid shift puts pressure on the skull and eyes. Many spacefarers have reported blurred vision after months aloft. In some, the shape of the eyeball actually changes, a condition now termed spaceflight, associated neuro-ocular syndrome. There is no up or down. After a few days, most adapt and can move around gracefully, but when they return to Earth, the process reverses. Suddenly they feel extremely heavy, dizzy, and weak. It's common for astronauts to faint upon standing after landing, due to O often reactivate in astronauts, indicating immunity isn't quite right. The landmark 1-year mission study of a twin astronaut found shifts in things like chromosome telomere lengths and gene activity during the long stay in orbit. Most of those changes returned to normal after some time back on Earth, a reassuring sign of resilience. Yet it demonstrated that the body truly is rewriting its operations to cope with space. Some changes were positively assuring, suggesting adaptation, but others raised questions about subtle long-term effects. Radiation plays a role as well. High-energy cosmic rays permeate spacecraft and can quietly damage DNA. And some astronauts indeed have developed painful kidney stones after flight. Back pain is frequently reported in orbit as the spine decompresses and lengthens. Sleep can be disrupted too, without a normal day, night cycle. And with the subtle physiological changes, many astronauts struggle with insomnia or fitful rest. Despite all this, humans can survive and function in space reasonably well for a time. We've learned to mitigate many issues: rigorous exercise fights, muscle and bone loss. Special lower body suction devices can pull fluids downward to relieve head pressure, and medications or dietary tweaks help with other imbalances. But the takeaway is humbling. Microgravity touches every system of the body, reminding us that we are creatures of Earth, trying to live away from it. If we truly wish to make space our home, we must redesign our homes or ourselves to account for this. Perhaps we create artificial gravity in our habitats to let our bones and muscles work. Perhaps we develop new medical therapies to prevent bone loss or enhance muscle growth in low gravity. Already, scientists study drugs like bisphosphonates to see if they help retain astronaut bone mass. We even consider genetic or technological augmentation in the far future. Could people engineered for space have stronger bones or radiation-resistant cells? For now, each person who slips free of gravity understands viscerally how much our bodies belong on the ground. One astronaut, drifting in the ISS, remarked on the strange freedom. "You feel like a ghost with no weight," he said, "but your body is working hard to adjust to that ghostly state." It is an ongoing adaptation, a testament to human plasticity, and also a warning. Our bodies can adapt to microgravity to an extent, but not indefinitely and not without support. Living in space long-term will mean continuously tricking or aiding the body, either through habitat design that simulates gravity or medical interventions that counteract the deleterious changes. We carry Earth with us in our flesh and bones. To live among the stars, we'll have to become shepherds of our own biology in a way never before required. The mind in space, isolation, psychology, and the need for connection. In the silent confines of a space habitat, it's not only the body that faces trials, the mind is tested in profound ways. Imagine months encased in a steel shell, with the infinite void outside and only a handful of other souls for company. No fresh breeze, no changing scenery beyond what the small porthole shows. This is isolation on a level few humans have experienced, and it can play tricks on the psyche. We are social creatures by nature, tied to the rhythms of Earth, the day-night cycle, the bustle of life, the comfort of Earth's ground under our feet. In space, much of that familiar context is stripped away. What does that do to a person's mental landscape? From studies in polar stations, submarine patrols, and simulated Mars habitats, we've learned that long-term isolation and confinement can lead to a cascade of psychological challenges. Mood and motivation can wax and wane. Small annoyances with crewmates, a loud habit, an inconsiderate remark, can fester in the pressure cooker environment where there's no easy escape from each other. Even those carefully selected for resilience and compatibility feel the strain. Astronaut crews are indeed chosen and trained with team dynamics in mind. They undergo team-building exercises and psychological evaluations to ensure they can handle living and working together for 6 or 12 months. Yet conflicts and tension are not unheard of, especially in longer missions. People can become withdrawn or irritable. In the famous year, Long Mars simulation studies on Earth, journals revealed how the crew went through periods of monotony, interpersonal friction, and homesickness. One striking phenomenon observed in long-duration missions is the so-called third quarter effect. When a mission is about 3 quarters completed, far enough in that the novelty has long worn off, but still not close enough to feel the excitement of near completion. Morale often dips sharply. Studies of 520-day isolation experiments noted stage-like patterns, an initial upbeat phase, a slump in the middle, then sometimes A and BH and play in their off time, finding solace in creativity. NASA also discovered the benefits of a simple garden, tending plants in space, watching leaves unfurl and flowers bloom, has a calming, morale-boosting effect. Several astronauts have spoken about the joy of smelling fresh leaves or touching soil, a sensory reminder of Earth that soothes feelings of alienation. One crew even celebrated when their small space-grown lettuce was ready to eat. That salad, though humble, represented life and normalcy in an alien place. Another powerful tool is journaling. Astronauts are encouraged to keep private journals of their thoughts and feelings, which they can choose to share later with psychologists to help understand behavioral issues. Writing offers an outlet to vent frustrations safely. Many crew members report that writing down worries or reflections helps keep them emotionally stable. It's like talking to a patient confidant who is always available, the blank page. Virtual reality and communication tech are also being explored to ease isolation. Imagine donning VR goggles and suddenly you're virtually sitting in your old living room with your family for a chat, or walking through a green forest path that feels almost real. Researchers are testing VR experiences as therapeutic escapes for crews on long missions. Early studies suggest this can indeed improve mood, a brief psychological vacation to earthly settings to relieve the confinement. Still, challenges remain that technology can't fully fix. Cultural differences can emerge in international crews. Misunderstandings might arise from different norms or language nuances. Crews must practice exceptional communication skills and empathy, developing a sort of family bond. When problems occur, they have only each other to rely on, a double-edged sword, because strong cohesion is protective. But if relationships sour, there's nowhere else to turn. Mission Control on Earth provides psychological support too, scheduling regular private conferences where astronauts can speak with a psychologist or counselor, and offering advice for team tension if needed. They also orchestrate morale boosts, occasionally surprising the crew with care packages, or coordinating simultaneous meals with family via video, link, etc., to keep spirits up. In deep space, beyond Earth's immediate vicinity, an additional psychological specter might arise: the Earth out of view phenomenon. Thus far, even on the Moon, astronauts could always see our bright planet hanging in the sky. But on a mission to Mars or further, there will come a point where Earth shrinks to a mere star-like point. Psychologists speculate that truly leaving Earth behind in that visual sense could induce a profound feeling of severance, an uncoupling from Earth that might cause anxiety or depression in some. One might feel unmoored, like an exile cut off from the collective human hearth. In literature and simulations, people have imagined that moment, a crew member staring out a porthole and no longer being able to identify which tiny dot is Earth. It's a moment of existential loneliness. Will future spacefarers find inner resilience and purpose to push through that? Or will some succumb to a kind of spacefarer's melancholia? Knowing this risk, mission planners are thinking ahead. How to prepare astronauts for that psychological shift, perhaps through training or through group discussions addressing the meaning of their journey. Interestingly, while isolation can harm, it can also engender unexpected strength and insight. Many astronauts report that in the struggle with solitude and confinement, they discovered new wells of creativity and spirituality. Some talk about the intense camaraderie that forms, a band of brothers, sisters feeling, where their small crew feels like an entire world and family unto itself. They celebrate each other's birthdays with genuine warmth and invent rituals aboard their spacecraft to create a sense of community. And upon returning, quite a few express a deepened appreciation for simple human contact, nature, and daily life. In a sense, the psychological challenges of space might make those who endure them more reflective, more grateful, and sometimes more connected to humanity than ever. In the end, the mind in space craves what it has always craved: connection, purpose, and a touch of the familiar. As we plan to live in space, equal attention must be given to building environments and routines that feed the human soul, not just keep the body alive. That means spaces that allow privacy when needed, means of communication that keep loved ones close in heart, and activities that give astronauts not just work, but life in space: music, art, humor, even intimacy and friendship. The stark void may surround them, but within their habitat, we must weave threads of home. Our psychology demands nothing less, because though we leave Earth, we carry all the emotional needs of Homo sapiens with us on the journey. The void of space is a grand frontier, but the void in one's heart must be kept filled with the light of human connection. That is as critical to survival as air and water. Artificial gravity, engineering gravity through rotation, Every evening on the space station, astronauts strap themselves to a treadmill and run, their bodies yearning subconsciously for the feeling of weight on their bones. As their feet pound the moving belt, their minds can almost trick them into feeling normal, almost, but not quite. True gravity remains absent. Yet, what if we could bring gravity with us into space? This question has been asked for as long as humans have imagined living off Earth. The most promising answer is both elegant and old in concept. Spin the spaceship. Artificial gravity by rotation relies on the simple physical principle that a rotating ring or cylinder will fling objects inside it outward, simulating the push of gravity. In a spinning habitat, down would be toward the outer hull, as centrifugal force presses inhabitants to the walls. Generations of science fiction films have depicted such stations, from slowly turning wheel-shaped stations to giant spinning cylinders with landscapes on their inner surfaces. In reality, we have not yet built a full-scale rotating habitat for people, but engineers have studied it extensively, and we have little doubt it can work. The challenge is how to do it practically in space in a rotating environment. You need a certain combination of spin rate and radius. If the radius is large, say a huge wheel a kilometer across, you could spin it gently, maybe only a rotation every minute or two, and the outer rim would provide near 1 G without making people dizzy. However, building something so vast in space is far beyond our current capabilities. If the radius is smaller, a more modest station tens of meters across, you'd have to spin it much faster to get 1 G, perhaps several rotations per minute. But humans are sensitive to rapid rotation. The inner ear can get upset, leading to motion sickness. Research from spinning room experiments on Earth indicates that most people can adapt to rotation rates up to perhaps 4 rotations per minute after some days, though at higher rates like 10 RPM, nearly everyone initially experiences strong disorientation. Fortunately, adaptation does occur. Test subjects who spent days in a rotating habitat on Earth found that after a while they could move normally without sickness at moderate spin speeds. But to be safe and comfortable, designers often aim for a spin rate of 4 RPM or less. At 4 RPM, to achieve 1 G, you'd need a radius on the order of 56 meters or so, a structure over 100 meters across in diameter. That's still huge, but potentially within the realm of future construction in orbit. Larger radii allow slower spin. For instance, a classic design from NASA in the 1970s, the Stanford Taurus scientists worry that even Mars's gravity might be insufficient to fully prevent bone and muscle loss, or to allow normal pregnant. The docking of ships to a spinning station is non-trivial. Perhaps you'd have to match rotation, or momentarily halt rotation for arrivals. There's also the matter of scale. To spin comfortably, bigger is better, but bigger means heavier and costlier to launch and assemble. We may need to master in-space construction, using robots or 3D printing, to build such megastructures piece by piece in orbit. Despite these hurdles, small, the allure of artificial gravity is strong because it directly tackles the root of so many problems. With gravity, astronauts would walk rather than float, giving their bones constant exercise. Fluids would settle normally, no more puffy faces and stagnant headward fluid. Showers and toilets would function more conventionally with weight to make water flow downward. Sleep might improve as the body feels the normal pull that it evolved to expect in rest. Eating and digestion would be simpler without food floating about. Essentially, it would allow a truly Earth-like living experience even in space. However, artificial gravity through rotation isn't a perfect recreation of Earth gravity. One quirk is the gravity gradient in a small spinning habitat. Your head, closer to the center, experiences slightly less centrifugal force than your feet. In a small radius, you might feel perceptibly lighter at your head than feet, an odd sensation. Also, any movement not purely tangential can cause Coriolis effects. For instance, in a spinning environment, if you drop an object, it won't fall straight down to the floor, but appear to curve a bit because of the rotation, something one would adjust to. If you turned your head quickly, you might feel a strange twisting in your inner ear, which can cause dizziness. But as experiments show, people can adapt to these as long as the rotation isn't too fast. After a day or two, many can function in a rotating room, almost as normally as in a static one. One can imagine the first rotating space city, a great wheel that spins in the void, sunlight streaming through its windows. Inside, children might play in a park with green grass, under a blue sky, created by centrifugal force, holding air and allowing clouds of water mist. Those children might not even realize at first that their world is artificial, except maybe when they notice that birds flying in the direction of rotation have to flap a little differently. The floor is curved, giving the S of a bowl. The horizon curves up. Yet they feel weight and can run and jump. For them, artificial gravity isn't artificial at all. It's just gravity, a constant companion, allowing life to flourish in space, as it does on Earth. In the nearer term, we might start smaller. Perhaps a Mars ship with a tether and a cargo counterweight, rotating slowly to give the crew maybe Mars level gravity during cruise. This could dramatically reduce the deconditioning they experience en route. They would arrive on Mars much readier to walk and work. A free-flying station in the 2030s or 2040s, built by commercial companies, might incorporate a rotating habitat module. Some have pitched designs like a dumbbell station, rotating to provide even partial gravity as a butt easier to shield against with proper shelter. Then there are the galactic cosmic rays, which are the nuclei of atoms accelerated by distant star explosions. These are extremely penetrating. They slice through spacecraft walls and human tissue alike, breaking DNA strands and knocking electrons from molecules. Over months and years, this cosmic rain can significantly increase one's risk of cancer and cause degenerative effects like cataracts or heart disease. There's even evidence from animal studies that cosmic rays might harm the brain over time, potentially impairing cognitive function or inducing neurological issues. Mice exposed to heavy ion radiation, akin to GCRs, showed memory and learning problems and signs of brain inflammation long after exposure. So when we speak of settling space, this is a silent threat we must address. A colony on Mars or a ship en route to Jupiter will be bathed in more radiation than any place on Earth. How much more? On the International Space Station, astronauts receive on the order of dozens of times the radiation per day that we get at sea level. A 6-month ISS stint might expose someone to around 50,100 times a chest X-rays worth of radiation dose. On a voyage to Mars, without Earth's magnetic field, that could roughly double or more. And in deep space beyond Mars, GCR flux is fully unleashed. Consider an extreme scenario. In August 1972, between the Apollo 16 and 17 moon missions, a massive solar flare erupted and shot out a storm of high-energy particles. Had astronauts been on the moon during that event without a thick shelter, they could have received a potentially lethal dose within hours. It was a lucky timing that no crewed mission was there. This event was a wake-up call. Any long-term habitat must provide a storm shelter where crew can hunker down during solar events, surrounded by extra shielding to absorb the sudden spike of radiation. Typically, water or special plastics are good for such shelters, since hydrogen, rich materials block solar protons well. On a Mars cruise ship, for instance, they might line a small closet or module with supplies that double as radiation absorbers, and crew would crowd in there for a few hours during a solar flare warning. For the chronic background of cosmic rays, more continuous shielding is needed. Shielding design becomes a crucial aspect of space architecture. Different materials have different shielding properties. Metals like aluminum stop some radiation, but when struck by cosmic rays, can produce secondary showers of particles that are themselves harmful. Research shows that hydrogen-rich materials are more effective because they produce fewer secondaries. This is why plastic materials such as polyethylene are excellent shields. They're full of hydrogen. Polyethylene is about 50% better than aluminum of the same mass at shielding solar flare radiation, and 15% better for cosmic rays. There's talk of incorporating plastic layers in spacecraft walls, or even using water itself as a shield. The walls of future habitats might include tanks of water or fuel that serve double duty, useful for life support, and also placed strategically to encircle crew quarters with a protective envelope. On Mars or the Moon, one obvious strategy is to use the local dirt. Martian colonists could shovel Martian soil on top of their habitats or live in structures. Just a meter or two of soil can cut radiation dramatically. The moon-based designs often include habitats covered by several meters of lunar regolith, blocking not only radiation but also insulating against micrometeoroid strikes and extreme temperatures. Innovative ideas are abound. Some propose inflating big plastic modules and filling their walls with water or even liquid hydrogen fuel. Great for shielding, but complex to implement. Others look at active shielding, generating magnetic or electric fields around a ship to deflect charged particles, essentially creating a mini magnetosphere. In theory, this could work, but the field strengths required are huge, demanding superconductors and power, and there's weight and safety issues. A study showed you'd need something like a 10+ Tesla superconducting magnet ring around a ship to significantly cut GCR exposure. That's technology we don't yet have for large scale. Passive shielding remains the go-to solution for now. So as we plan habitats, we deliberately design in thick walls, especially around sleeping quarters where people spend lots of time. For example, spacecraft may put storage modules around crew quarters to act as buffers. There are trade-offs. You can't shield everything heavily or the mass becomes prohibitive. Thus, mission planners set exposure limits. Under those limits, a Mars mission is borderline. Some scientists say current shielding plus travel time would lead many astronauts to reach or exceed safe limits, which is partly why reducing travel time and adding shielding is key. On the surface of another world, like Mars, radiation is still a concern. Mars has a thin atmosphere that offers only modest protection. It also lacks a global magnetic field, so settlers there would get a chronic dose roughly several times higher than on ISS. Over a year, that could be significant. They will likely live in habitats that might be built into Martian hillsides or covered with sandbags of Martian soil for safety. The romantic notion of a glass-domed city on Mars conflicts with radiation reality, unless that glass is actually a multi-layer composite with radiation absorbing layers. Even then, during a solar storm, colonists might have to retreat to deeper shelters. Some plans foresee underground habitats in lava tubes where meters of rock overhead naturally block cosmic rays completely, a very attractive refuge, though cave living has its own challenges. Radiation does more than increase cancer risk. It can weaken the body in subtle ways. For example, astronauts have reported changes in their blood counts and hints of impacts on their immune system after long flights. Cataracts have appeared earlier in some astronauts' lives, likely from space radiation exposure. There's concern about fertility. Cosmic rays could damage sperm or egg cells, or harm a developing fetus. If we imagine multi-generational space communities, we must solve radiation protection for the unborn and children, who are especially sensitive to radiation's effects on growth and DNA. That might mean particularly heavily shielded nurseries and schools in any space settlement, maybe literally encased in water tanks or regolith for extra safety. Hope lies in clever engineering. A combination of passive and active techniques could bring radiation down to levels comparable to what high-altitude pilots or miners on Earth face, still above normal background, but perhaps manageable. The Artemis Accords, an international guideline for lunar exploration, explicitly state that resource extraction for shielding is allowed. Countries and companies know that without addressing radiation, sustainable presence is impossible. So, lunar base concepts often include robot-built berms of soil around landing pads and habitats. The first habitats on Mars might be 3D, printed from the local dirt, forming thick walls, even if the inside is pressurized inflatable sections. In orbit, a possible intermediate solution is a storm shelter module on stations, as mentioned, basically a small, heavily shielded safe room. Already on ISS, there is procedure during solar flares. Crew go to the most shielded parts of the station and avoid spacewalks. Future deep spaceships will definitely have a designated spot with extra shielding for such events. But day to day, the whole living space needs reasonable shielding too to avoid cumulative harm. Beyond technology, we may also rely on medicine. Pharmaceuticals like radioprotective drugs are being researched, pills that could bolster cells' resistance to radiation or scavenge free radicals caused by it. On Earth, certain drugs are given to people undergoing radiation therapy for cancer to protect normal tissues. Perhaps spacefarers will take a daily rad shield pill. Even dietary antioxidants are suggested to help mitigate radiation damage to some degree, so diets might be adjusted. However, these are supplementary at best. Nothing beats physical shielding to stop the particles from hitting you in the first place. In summary, radiation is one of the most formidable barriers between us and comfortable life in space. But it's a physics and engineering problem we can solve. Thick materials, smart placement of resources, and possibly active deflection systems will together form an umbrella over future space habitats. In the black of space, you can imagine seeing a faint blue-green glow around a large spaceship, maybe an artificial magnetosphere at work, or shielding panels glittering. Inside, children play without fear, not realizing that beyond those walls, lethal rays are being tamed. On the moon, colonists might live in habitats that to an outside observer look like mounds of dirt. Humble burrows that hide vibrant human homes safe from the sun's tantrums. When we finally set sail to the stars, our starships will likely resemble castles with thick walls, carrying an inner Earth with them. We will make our own magnetic fields and carry our ocean water as protective moats. In this way, we extend the protective womb of Earth around each off-world outpost. By doing so, we declare that even in the most inhospitable reaches, life will not only travel, it will thrive, wrapped in shields against the ancient cosmic storm. Just as our ancestors wore furs against the cold, or built roofs against the rain, spacefarers will don radiation armor in myriad forms, and thus endure and prosper under alien skies. Meglio. Life support. Build enclosed loop systems. In the tiny ecosystem of a spacecraft, every breath is precious. Exhale, and the carbon dioxide must be scrubbed away. Inhale, and you hope the oxygen you need has been regenerated. Far from Earth, the luxury of an endless open-air reservoir is gone. Instead, living in space becomes an exercise in self-contained life support, a delicate dance of recycling and renewal. To truly live in space, not just survive on supplies, we must build closed-loop systems that mimic Earth's great recycling feats on a miniature scale. On Earth, plants constantly turn CO2 into oxygen. The water cycle endlessly purifies and redistributes moisture, and bacteria break down waste into soil nutrients. Our task is to replicate those services in our spacecraft and habitats, effectively creating a tiny Earth wherever we go. The ultimate goal is often described as closing the loop, meaning all human waste outputs are converted back into inputs with minimal resupply. In a closed-loop life support system, a community could potentially live indefinitely using local resources and robust recycling without needing constant supply ships. We've already begun inching towards this aboard the ISS. The station's life support can reclaim about 90% of water used. Every drop of humidity in the air from sweat and breath, every drip of condensation, and yes, processed urine too, all are with hydrogen to produce water and methane. The water is then split via electrolysis to make fresh oxygen. This loop helps reclaim oxygen from CO2, though it's not 100% closed. The methane is vented as waste. so some hydrogen is lost each cycle. Future systems might better utilize that carbon and hydrogen. Right now, about 40% of the oxygen on ISS still comes from tanks or oxygen, supply cargo. But advanced regenerative life support aims to push that closer to 100%. NASA and other agencies are actively working on more efficient regenerative ECLSS, because for missions like Mars or a lunar base, resupply will be costly and rare. The vision is a robust system where the crew's urine can be processed not only into water, but also nutrients, where perhaps algae or special bacteria take in the CO2 and produce edible biomass or oxygen. This edges into the concept of bioregenerative life support, incorporating living organisms to do some of the recycling heavy lifting. For instance, a greenhouse module on a station could grow vegetables, yielding food, while absorbing CO2 and releasing O2, and perhaps using grey water for irrigation. Astronauts get fresh salads, and the system loops resources. There have been experiments like the Russian BIOS 3 facility decades ago, where 3 humans lived in a sealed environment sustained largely by wheat and chlorella algae they cultivated, which recycled air and water. They achieved a high degree of closure, though they still needed some external inputs. Lessons from those experiments inform today's designs. A fully closed life support system is incredibly complex. Think of all the things that must be balanced: oxygen levels, CO2 removal, trace contaminant control, water purity, nutrient recycling, temperature, pressure, and so on. On Earth, an entire planet's worth of processes handle this. In space, we'll rely on tanks, filters, reactors, and maybe greenhouses tucked into a habitat corner. It's both engineering and ecology, essentially creating a miniature ecosystem. One dramatic story that underscores the difficulty is Biosphere 2, the large sealed dome in Arizona, where 8 people attempted to live for 2 years in the early 1990s. They had an entire 3-acre biome with plants, soil, even small animals. Yet, unexpectedly, oxygen started dropping dangerously. They had to break closure and inject O2 mid-mission. It turned out the concrete in the structure was absorbing O2, something the designers hadn't fully accounted for. The biospherians also grew hungry because farming wasn't as productive as anticipated. They did survive the 2 years inside, but the experiment revealed how many hidden variables exist in a closed system. It was a reminder that closed-loop life support is hard, but also valuable, because we learned what not to do and the importance of careful monitoring of each element. In space habitats, we likely won't try to replicate an entire rainforest and ocean like Biosphere 2 did. Instead, life support might be a hybrid of mechanical and biological. Mechanical systems are very good at certain tasks, e.g., filtering water, scrubbing CO2 with chemical sorbents, and they are compact. Biological systems are good at multitasking. A plant can purify water through hydroponic uptake, generate oxygen, sequester CO2, and produce food, all in one organism, given light and nutrients. But they can be slower and less controllable. Plants might grow unpredictably or be susceptible to disease. A safe approach might be to have core mechanical systems for immediate needs and robust control, augmented by a greenhouse that contributes gradually increasing closure as it matures. For instance, imagine a Mars base. Initially, it relies on stored oxygen and water recycling units brought from Earth. But as they set up greenhouses and maybe bioreactors with algae, they start cycling more and more internally. The greenhouse provides fresh food and a supplemental oxygen flow. A bioreactor with algae could take human waste and via microbial action convert it into methane and fertilizer, or even directly feed algae that produce more edible biomass. It's a bit unappetizing to consider, but future waste treatment might literally mean turning yesterday's waste into tomorrow's breakfast. Nothing can go to waste in a closed loop. Even human solid waste might be sterilized and used as compost for crops. In the ISS right now, solid waste isn't recycled. It's packed into disposal craft that burn up in the atmosphere. On a colony, that would be like throwing away valuable carbon and nutrients. We'll want to use it. A closed loop also implies independence from Earth's supply chain. It's not just environmental closure, but also resource self-sufficiency, manufacturing spare parts on site, growing what you need. For example, rather than shipping tons of clothing, perhaps future habitats will have machines to weave fabric from plant fibers grown in the greenhouse, or recycle fibers from old clothes. These ideas blur into the economic and industrial loop closure, not just life support in the narrow sense, but they're intertwined. A truly closed system would import nothing but energy and perhaps raw materials from local sources, and export nothing but maybe excess heat or information. NASA often talks about steps. Atmospheric revitalization. We have partial closure solutions. Water recovery. We are close to full closure. Waste management. The least closed currently. But new tech like the ESA's Melissa project has multi-compartment bioreactors that break down waste and grow edible spirulina algae from it. They've demonstrated that it can work on a pilot scale, producing clean water, oxygen, and protein-rich algae from synthetic waste streams. In the coming decades, such systems might be incorporated into stations and bases. A crew might eat a portion of their protein as algae or insect meal grown from waste. Not the most glamorous diet component, but it could be efficient and healthy. Meanwhile, higher plants supply psychological satisfaction and dietary variety. One could foresee a Mars-based greenhouse with tiers, fast, growing algae in tubes, sturdy leafy greens in hydroponic trays, vine crops like tomatoes or beans twining under LED lights, maybe dwarf fruit trees if space allows for morale. Those plants would churn out oxygen and fresh flavors while sucking up the CO2 the crew produces. Water circulates between fish tanks, plant beds, and filters. In a corner, a machine quietly dehydrates and pulverizes solid waste to feed into a biodigester. Nothing smells foul because it's all well contained and managed. One hopes. Keeping odors and hygiene in closed systems is also crucial. Filters for smell are part of life support too. Life support also involves maintaining air pressure and composition. Spaceships must keep roughly sea level pressure and about 21% oxygen, 78% nitrogen. Nitrogen is inert ballast, but important, so a closed loop must conserve nitrogen as well. Fortunately, nitrogen isn't consumed by humans, but leaks could lose some. Martian atmosphere is mostly CO2 with some nitrogen. A base could extract that nitrogen to fill its habitat initially. If we master closed-loop life support, the implications are huge. It means a colony could survive even if supply lines break, which is ultimate resilience. It also means the mass burden for resupply goes way down, making deep space exploration feasible. For a trip to Jupiter that might last 5 years, bringing all the oxygen and water would be impossibly heavy. Regenerative systems make it conceivable. In the long term, as human communities settle space, their life support might become not just utilitarian, but lush. Imagine an O'Neill cylinder where the entire interior surface is basically a living ecosystem. That is life support at its most advanced and pleasant, where you don't think of it as machinery at all, just an environment that naturally sustains you. But to get there, we will perfect these closed systems bit by bit in smaller stations and bases. We will learn to be gardeners of the life loop, tending to our mechanical plants and biological ones alike to keep the delicate balance. A poetic way to view it. As we leave Earth, we must carry Earth with us in our ships, not literally soil and oceans perhaps, but the essence of Earth's renewing powers. In our starships will bloom little Earths, algae as green as any forest moss, water cycling like Minnie, rainfalls in clear tubes, and machines humming like diligent microbes. We become curators of our own biosphere in microcosm. In doing so, we appreciate all the more the grand closed-loop system of our homeworld. Many astronauts, after seeing how complex and careful life support is on the ISS, remark that it made them marvel at Earth's ecosystems that do it all naturally and seamlessly. So, to live in space, we learn to bottle the sky and the sea and the soil, to make them travel, sized, and reliable. With each improvement in life support, the umbilical cord to Earth stretches thinner. One day, it may break entirely when a colony stands fully self-sufficient. And by then, that closed loop will essentially be an offspring of Earth's biosphere, a self-contained bubble of life traveling afar. Humanity's survival in space will hinge on these systems, on whether we can truly become, in effect, the ecosystem for ourselves. It is perhaps the greatest engineering and agricultural challenge we've ever undertaken. But step by step, recycling tank by recycling tank, seed by seed, we are getting there. In a very real sense, learning to live off-world is teaching us how to be better stewards of resources, which ironically circles back to help Earth too. After all, if we can recycle 98% of everything in a space colony, why not on Earth? The closed-loop technologies might one day help cities on our home planet become more sustainable as well. Thus, space life support and Earth environmentalism go hand in hand, each inspiring advances in the other. Space habitats, inflatable stations, modular cities, lunar domes, Mars bases. In the vacuum of space, or on the barren surface of another world, human habitations will be our cocoons of life. Building a space habitat is unlike construction on Earth. Here, our structures must provide not just shelter from weather, but protection from vacuum, radiation, and extreme temperatures, all while delivering air, water, and power to those inside. Over the decades, engineers and dreamers have conceived many forms for these homes beyond home. Inflatable modules that expand like balloons, modular structures that connect into orbiting cities, gleaming domes on the moon, or interlinked habitats on Mars, forming the first outposts of civilization there. One exciting development in recent years has been the testing of expandable station modules. Traditional spacecraft modules are rigid metal cans, limited in diameter by what a rocket can fare. But an inflatable can be launched compact and then expanded on site to create a far larger volume. The Bigelow Expandable Activity Module demonstrated this on ISS, packed tight during launch, then blown up into a cushioned room in orbit. It showed that fabric walls could hold pressure and withstand micrometeoroids effectively. It also proved resilient to orbital debris strikes, performing as well as solid aluminum in tests. Inflatable habitats offer big living space for relatively low mass and launch size, a huge boon for building roomy stations. Concepts like Bigelow's BA-330 envisioned private space hotel modules with 330 cubic meters of volume each that could link together. NASA's earlier Transhab concept imagined an inflatable for the ISS that never flew, but the idea survived and thrives now in new designs. Companies like Sierra Space are continuing this work with their planned Life Habitat, a 3-story, tall inflatable module that could form part of a commercial space station. Inflatable stations might well become the norm, enabling something like an orbital city made of multiple bubble-like modules joined by corridors. Each module could be dedicated, one a greenhouse bubble, another crew quarters, another a laboratory. They can be added as needed, like adding extra domes to a colony of bubbles. Meanwhile, the ISS itself is the archetype of modular construction in space. It was assembled piece by piece, each launched separately and connected by astronauts. This modular approach will likely continue. It gives flexibility and incremental growth. A modular city in orbit might start with a core and then branch out with additional modules docked in multiple directions, like a growing organism. It could be reconfigurable, moving modules around or adding new arms as population grows or new functions arise. Already the ISS partners plan successors. Smaller modular stations in low Earth orbit, perhaps one around the Moon. These will use standardized interfaces, akin to how shipping containers on Earth are standardized, so any new module from any participating nation or company can attach with relative ease. In future orbiting settlements, one might see a mix of inflatable habitats attached to a rigid backbone that supplies power and attitude control. On the Moon and Mars, habitats must contend with gravity, dust, and terrain. Lunar domes have long been a staple of science fiction art. Transparent or opaque domes covering a habitat or even an entire colony crater. In reality, a large glass dome would struggle with radiation exposure and micrometeorites, but smaller domes or tensile fabric structures under regolith shielding are considered. One idea is to land an inflatable on the Moon, then pile moon dust over it using robotic bulldozers, essentially burying it for protection. The result might appear as a mound from outside, but inside a spacious dome ceiling, perhaps with internal lighting to feel like a sky. A lunar dome could also refer to rigid half-cylinder structures covered in lunar concrete or sandbags. European researchers have tested 3D printing with simulated moon dust and found they can create sturdy arch shapes and bricks. Imagine a lunar base where robots 3D print a thick half-dome shell on the surface. Then astronauts arrive and place a pressurized living module under that shell. Now the module is protected and can have windows that open into the interior of the dome. Mars bases similarly revolve around using local materials. Mars has atmosphere so inflatable, greenhouses might actually balloon outward there. Designs for Mars habitats often show cylindrical modules set on the ground and connected by tunnels. Picture a cluster of white or silvery cylinders, half buried in Martian soil, linked by covered walkways. Each cylinder might be a few meters in diameter and 10,015 millers long, basically an oversized railway car. Mars base plans from agencies typically start with 2003 modules landed on pre-chosen flat terrain, connected to each other. Eventually more are added, plus specialized ones. Over time, this could expand to a small village. Modularity again is key. Early bases might literally be repurposed spacecraft. NASA's concept of Mars Ice Home is an inflatable dome structure that would then be filled with water ice as a thick, transparent radiation shield around living space. A fusion of natural material and human tech, resulting in a dome that glows blue with ice, insulating the people inside. Crucially, all these habitat designs consider airlocks, how people get in and out without depressurizing the whole living area. Orbital stations have docking ports as airlocks for spacecraft and dedicated smaller compartments for spacewalkers. On a planet, airlocks are like mudrooms. One door leads out to vacuum or thin air, one leads in. You cycle the pressure in between and perhaps have a suit donning area. For the Moon, regolith dust is a menace. Apollo astronauts got their suits covered in abrasive dust, which they then tracked into the lunar module, causing irritation and equipment issues. Future lunar habitats might incorporate suit ports, basically suits that dock onto the outside of an airlock. An astronaut opens a hatch, climbs directly into the back of a suit, and detaches to go outside, leaving the dust on the suit, which stays mostly outside. Such clever innovations will shape habitat layouts. Speed of deployment is also important. An inflatable or prefab module can be set up quickly. For instance, imagine landing an autonomous habitat on Mars a year before crew. It has solar panels and starts warming itself up and producing oxygen via a reactor using Martian CO2, maybe storing it. By the time humans arrive, they have a livable ready base with stocked air and water, a pre-deployed habitat. This is the strategy of many Mars mission profiles. Send cargo and habitat first, ensure it's functioning, then send humans. The habitat might even drive itself a short distance to a better location. On Mars, Using local CO2 and hydrogen brought from Earth to make water and methane fuel is planned. The same plant can fill habitat tanks with oxygen. Scaling up from small bases to true cities is a huge leap, but one can envision incremental growth. A research outpost of 6 people in 2 modules grows to 30 people in 8 modules over years. Then they build more permanent structures. Eventually, you might have interconnected lava tubes, serving as natural tunnels, housing hundreds, sealed at some points by bulkhead doors, and with farms and living quarters inside. A Martian city might mostly be underground for radiation safety, but with some skylights or surface domes with thick glass or ice for natural light in communal areas. Orbital cities like O'Neill's cylinders are further out, but remain a goal in many minds for 50,100 years ahead. Those would be kilometers long, spun for gravity, holding thousands. Getting to that scale likely requires substantial industrial presence in space. We're not close yet. Instead, nearer term we might see something like the proposed Voyager station by a private group, a rotating ring station of smaller modules accommodating maybe a few hundred tourists, essentially a big wheel with habitation pods along it. It's concept art now, but it's based on known physics of artificial gravity. If our inflatable tech and modular tech converge, building a ring out of connected inflatables might be plausible. Spin it up, and voila, a station with gravity. Lunar bases might also become more modular and city, like if multiple countries set up camps near each other. One can imagine an Artemis base camp merging with another international base, forming a little village of habitats, connected by pressurized tunnels or frequent rover commutes across the surface between them. We have to also consider support infrastructure. Power sources sitting adjacent to habitats, likely connected by cables. Landing pads a safe distance away, perhaps roads or tracks between facilities. Even something like a rail system or conveyor to bring regolith to a processing plant might appear. In short, a true habitat isn't just sleeping quarters. It's an integrated settlement with utility lines, storage tanks, garages for vehicles, and emergency shelters. One fascinating concept for Mars is the Mars-based 3D Printed Habitat Challenge by NASA, where winners designed habitats printed from Martian soil and ice. One winning design was a multi-layer dome, an outer shell of ice for radiation shielding, an inner dome of pressurized living space, and vertical silo living quarters inside with multiple levels. It looks like an elegant igloo palace. Another design featured modular pods that could be printed and connected, resembling a cluster of giant pebbles. These creative ideas all revolve around using in situ materials to expand beyond what we could bring. Dust and maintenance are also a reality. Our habitats must be robust. Everything leaks slowly. Careful monitoring of pressure and plugging of micrometeoroid punctures will be routine. Dust seals on airlocks and moving parts must be meticulous on Moon Mars, because dust can foul them. The materials of the habitat, whether layered Nextel, Kevlar, and Mylar fabrics for inflatables, or regolith-based concrete, must endure years of cosmic ray exposure and temperature swings. So, for longevity, covering habitats with soil is beneficial not only for radiation, but also to keep interior temperature stable and protect the structure from UV and thermal stress. In sum, the architecture of living in space will be an evolving blend of high-tech fabrics, metallic nodes, and native soil turned into construction material. Early on, it might look provisional, metal cans under dirt piles, or balloons inside craters. But as we refine techniques, these could morph into habitats as comfortable and secure as Earth buildings. Future generations might play soccer in a pressurized lunar lava tube illuminated by arrays of LEDs mimicking Earth daylight, or stroll through an orbital habitats park, forgetting for a moment that just meters away is the void. We humans have always adapted our shelters to environments. Think of igloos in the Arctic, clay houses in deserts, stilt houses over water. Space and other planets are new environments demanding new architecture. Our habitats will likely be modular, reconfigurable, and organic in their growth, a living architecture that starts small and builds up. They might start utilitarian, but as populations stabilize, we'll add aesthetic touches, maybe big windows with protective glass, or art and color on interior walls to break monotony. Even in a Mars base, one could paint a ceiling with a blue sky and white clouds motif to psychologically enlarge the space. One day, the phrase "home sweet home" might apply equally to a geodesic dome on Mars or an inflatable torus in orbit, as it does to a cottage on Earth. Our space habitats are the eggshells in which the fledgling off-world society will grow, initially small and fragile, but destined to get bigger and stronger. With each successful habitat, from a 2-person lunar hut to a 100-person orbital outpost, we gain confidence that we can build a home anywhere. These first habitats are pathfinders that teach us how to create shirt-sleeve Earth, like environments in places utterly alien. When future historians write of humanity's expansion, they might trace it through the lineage of our habitat designs, each more ambitious than the last, turning inhospitable wilderness into places of warmth, air, and life. Orbital stations, constant motion, speed, and the edge of Earth. High above Earth's atmosphere, orbiting stations slip around the planet at breathtaking speeds. To the astronauts aboard, however, life in an orbital station can feel strangely static, a home that continuously falls around Earth, offering an unending view of sunrise and sunset every 90 minutes. These stations are our stepping stones into space, artificial islands circling in the void at thousands of meters per second. They represent the first true attempts at living off Earth for extended periods, and they have taught us volumes about what it means to call space home. Consider the numbers. The International Space Station whips along at about 28,000 km/h, completing an orbit roughly every hour and a half. To its crew, this motion is imperceptible except by looking out the window. The ground below racing by, 16 sunrises and 16 sunsets each day. The station's microgravity environment is a direct result of this perpetual free fall around Earth. An orbital station is thus a place of paradox, tremendous velocity and dynamic movement through space, yet relative calm and stillness within. It's as if being on a smoothly flying jet, one doesn't feel the speed, only sees the world blur by outside. Orbital stations like Skylab, Mir, and the ISS have progressively grown more sophisticated. Skylab was essentially a repurposed Saturn V upper stage, a single large workshop that hosted astronauts for up to 84 days. Mir was modular, with multiple rooms docked together, and supported multi-month and even year-long stays. The ISS, a global collaboration, is the largest, about the size of a football field if you include its solar panel span. It has multiple laboratories, crew quarters, even a cupola window dome to observe Earth. The ISS has been continuously occupied for over 20 years, a testament to reliability and international commitment. It truly hugs the edge of Earth, technically still in low Earth orbit, often about 400 kilometers high, where Earth's presence is visually dominant but physically absent. Life on an orbital station is dominated by that unique setting. Constant motion, no up or down, Earth always in sight. Astronauts often remark on the overview effect, the profound shift in perspective seeing our planet as a single fragile globe. On a station, you get that view every day. One moment you see the bright blue Pacific, half an orbit later, the darkness over Africa with city lights sparkling. The thin atmosphere appears as a delicate glow on the limb, reinforcing how special Earth is. This psychological impact has arguably been one of the greatest contributions of orbital stations, how they change those who live there, instilling a deep awareness of Earth's unity and fragility. Many crew members become ambassadors for environmental protection after their missions, precisely because, from their vantage point, they saw the paper, thin atmosphere shielding all life. Stations move fast and also experience microgravity permanently. We've discussed how microgravity affects the body. Here, we consider how it defines the habitat and daily life. It's as if being on a smoothly flying jet. One doesn't feel the speed, only sees the world blur by outside. Orbital stations like Skylab, Mir, and the ISS have taught us how to live in perpetual free fall. Daily life on a station is regimented, yet surreal. Astronauts float from module to module, tacking their toes under handrails to stabilize themselves at work. There is no true up or down. They might sleep in a vertical orientation and work on a wall. They learn to orient by agreements. The station's layout becomes a three-dimensional maze, with air vents quietly whooshing, equipment humming, and laptops velcroed to surfaces. Constant motion means constant microgravity, which shapes every mundane task. Drinking requires sealed bags or straws. Salt and pepper come in liquid form to be sprinkled. And cleaning involves chasing down every crumb and drop that could drift into electronics. Even something as simple as cutting hair is an operation. One crew member uses clippers attached to a vacuum hose to suck away the snipped bits of hair, lest they flit about like dandelion seeds in the cabin. Though busy with science and maintenance, station dwellers make time to appreciate their unique vantage point. In the ISS cupola, a multi-windowed dome looking down at Earth, astronauts gather like souls at a campfire, except their fire is the radiant planet below. They press their faces to the windows to watch thunderstorms flicker, auroras shimmer in green ribbons along Earth's atmosphere, and familiar continents slide past under day and night. Many describe moments of floating there in silence, awash in awe and homesickness all at once. On the edge of Earth, they become keenly aware of its beauty and fragility. One can imagine future orbital citizens experiencing the same daily wonder, waking up to a sunrise that covers the whole horizon in seconds, or pointing out to a child where their grandparents' country is as it comes into view far below. Orbital stations must also constantly mind their environmental systems. Crews on the ISS spend hours maintaining life support equipment, swapping CO2 scrubber filters, fixing the water recycler. They live with the awareness that just a thin hull separates them from the vacuum. It's a safe home, but a tended home, one that demands vigilance. When a warning alarm rings, everyone stops and responds methodically, checking pressure readings, donning emergency masks if needed. Drills are run for fire or ammonia leaks. In 2 decades, serious emergencies have been rare, but crews train relentlessly for them. This is part of life in an orbital outpost. You become not only a resident, but also a constant caretaker of your habitat. In the future, perhaps more systems will be automated or built with redundancy to ease this burden. But likely, station crews will always have some janitorial duties for their floating colony. One day, orbital stations might transition from research bases to commercial hubs or even tourist destinations. Designs like a rotating hotel with artificial gravity at its rim have been proposed, as well as free, flying private stations composed of inflatable modules. In those, everyday life might incorporate more leisure, perhaps a space lounge with a wide window where guests sip beverages from magnetic cups while gazing at Earth, or a small zero-G sports arena where humans can experience graceful somersaults and games of 3-dimensional tag. What is constant is the backdrop of speed and Earth's curvature. Even for a tourist, the first time they unstrap and float freely must be astonishing. The body initially panics with a sensation of falling, but then delight takes over as you realize you can fly from one end of the habitat to the other with a gentle push. Laughter, we can imagine, will echo through future orbital halls as newcomers bounce around like children in a playground, finding the sheer joy in microgravity motion. Communication on orbital stations is near instant with Earth. Crews talk daily with mission control, They even make IP phone calls or video links to family. This closeness in comms and relative proximity maintain a strong bond with home. They know if something goes very wrong, a Soyuz or Dragon capsule can bring them back to Earth in a matter of hours. Orbital living is thus a liminal state, neither fully on Earth nor fully away. It's perhaps akin to living on a ship in sight of shore, distant but not isolated. As we move outward, stations around the moon will lengthen that tether, a few seconds delay in communications, and days of travel from Earth. Eventually, a station orbiting Mars would be truly frontier, 8-month travel time to reach, and radio signals taking 10 to 20 minutes one way. By then, an orbital station might have to be more autonomous, a self-sustaining community. For now, the ISS remains humanity's shining example of a sustained home off Earth. It circles endlessly, a bright star crossing twilight skies if you know when to look. Many people on the ground have stepped out to wave at that moving dot, knowing human beings are up there. Inside, those humans might at that moment be having dinner, squeezing mac and cheese from a pouch and rehydrating a tortilla, maybe playing music on a guitar. They might be joking with a crewmate about a glitch they fixed earlier, or planning tomorrow's science tasks. Perhaps someone is writing in a personal journal by the dim reading lamp, recording feelings for which there are no easy words. Over the years, journals from space have revealed how much astronauts ponder existence, miss their families, revel in the view, and even dream of floating. Some report they still dream they are weightless after returning to Earth. The orbital life has its own rhythms: work, exercise, rest, all carefully scheduled, yet the extraordinary lurks at every window glance. Looking ahead, we see orbital stations growing more permanent and populous. We might go from 6-person crews to 50-person communities in large rotating habitats by mid-century. These could become the first true space settlements, with engineers, scientists, teachers, maybe even artists or caregivers living on board for years, potentially raising families in orbit. The line between spacecraft and colony will blur. Already, the ISS is an international village of sorts. Russians, Americans, Europeans, Japanese, Canadians working and living together in a tight space, sharing meals and stories. In the future, orbital communities may develop their own micro-culture, unique slang, celebrations of station milestones, maybe even traditions like an orbital sunset party every Friday where residents gather to watch a particularly beautiful sunset and play music. Such a life is not for everyone. It requires tolerance for confined quarters and distant horizons. But those who do live there often describe it as profoundly fulfilling. Every day, I looked out the window and saw something that made me grateful to be alive, one ISS veteran said. Another confessed that returning to Earth's gravity felt strange and constraining. They had adapted so well to fall freedom that walking was almost disappointing. From these anecdotes, one gleans that constant motion in orbit leads to constant adaptation. Humans truly learn to live anew, and live they do, not just exist. They find camaraderie in their crew, beauty in their tasks, and a sense of participating in a grand human endeavor. An orbital station is more than a lab. It is a community in motion, forever voyaging around our world and reminding those on board that home can be wherever we build it. Moon bases: dust, light, and permanence. On the dusty plains and crater rims of the moon, humanity envisions its first footholds beyond Earth. A moon base would be our initial attempt to live permanently on another celestial body, a place with gravity, soil, day and night, yet utterly alien and inhospitable. The challenges of the moon are distinct: the peculiar daylight cycle, the pervasive razor-sharp dust, and the question of how to make a settlement truly permanent in a place long thought of as desolate. And yet, the moon offers tantalizing advantages. Nearby resources like water ice in shadowed craters, a quiescent geology, and proximity to Earth that makes it the logical training ground for further outposts. One of the Moon's greatest challenges is its dust. The lunar regolith is not like soft Earth sand, without water or air to weather it. Each particle is jagged, gritty, and sticks to everything. The Apollo astronauts discovered this to their dismay. After bounding about on the surface, their suits were coated in fine grey powder that smelled like spent gunpowder and clung stubbornly. The dust worked its way into suit joints and seals, causing wear. Some astronauts suffered lunar hay fever, with sneezing and throat irritation when they inhaled the dust carried into the lunar module. Future moonwalkers in a base will likely face the same nuisance amplified because they'll be doing hundreds of EVAs, not just a few. Mitigating lunar dust will be crucial. Engineers have plans, spacesuit airlocks or suit ports to keep dust out of habitats. Also, cleaning protocols might involve using electrostatic wands or brushes to push dust off suits, or sticky mats at airlock entrances to capture particles. The base interior could be maintained at slight positive pressure so that if there's any leak, air flows out rather than dust blowing in. Additionally, the living quarters might be elevated or isolated from the surface, for instance, connected by enclosed tunnels to minimize direct contact with dusty ground. However, dust will inevitably find a way in. Thus, materials inside the base must be chosen to resist abrasion and be easy to wipe down. Air filtration systems will constantly scrub floating particles. Moon dust is not toxic in itself, but over long exposure, it could cause lung issues. So base design treats dust almost like a hazardous material to be carefully contained. Despite these challenges, no one suggests avoiding the moon due to dust. Rather, we adapt as explorers always have. We will likely deploy simple solutions like regolith, covered garages for rovers, where they can shed dust away from the main habitat. Next is the matter of light and darkness. Unlike orbit, where the sun rises every 90 minutes, on the moon, a day lasts 29.5 Earth days. At the equator, that means roughly 2 Earth weeks of blazing sun, then 2 weeks of frigid darkness. The temperature swings are enormous. 120 degrees in day, 170 degrees at night. Surviving the night is a major design hurdle. It requires either storing ample energy or having a nuclear power source, as solar arrays produce nothing during the long lunar night. One solution is to establish bases near the poles, especially the South Pole. There, due to the moon's slight axial tilt, some mountain peaks receive near, continuous sunlight. This is a boon for solar power. Farms of solar panels on ridges can bask almost all month, needing minimal batteries. Likewise, some craters at the poles remain in permanent shadow and trap ice. So at the South Pole, you have 2 vital resources side by side: sunlight and water ice. That's why current plans target the South Polar region for a base. If you set up on a well-lit ridge, you can tap constant power and endure no long nights. Even with abundant sunlight, the angle of light is shallow, casting long, eerie shadows. A base might get sunlight at a low slant, which could complicate things like charging batteries or heating certain sides of habitat. But engineers can arrange rotating solar panels or mirrors to direct light where needed. The pole offers relative thermal stability too. In perpetual light areas, temperature stays around a constant 50 to plus degrees range, easier to manage than the equatorial swings. Still cold, yes, but a base can be insulated and warmed with sunlight. One imagines a polar moon base perched on a crater rim, the landscape bathed in a near, constant dawn, like glow. Surrounding the habitat are glittering solar arrays on tall masts that rotate to face the sun. Cables snake from these arrays to modular shelters half, buried under regolith for radiation shielding. Nearby, maybe just a few kilometers down, slope in shadow, robotic miners scoop up regolith and ice chunks from a crater floor, hauling them to a processing plant. There, the ice is melted and split into hydrogen and oxygen, rocket fuel, and also water for the base. At times, humans might go down to assist, or set new explosives to break ice. But likely much of that work is automated, to keep astronauts mostly in the light and out of extreme cold. Radiation on the Moon is a concern due to lack of atmosphere. As discussed earlier, thick shielding is needed for full protection long term. Covering habitats with moon dirt is the simplest approach. Designs show cylindrical or dome habitats buried under several meters of regolith, perhaps placed inside excavated trenches or pits to make burial easier. This has the side benefit of protecting from micrometeorites and insulating against temperature changes. A buried lunar habitat might not have windows, but perhaps periscopic devices or external cameras can bring in views. Alternatively, some sections could be left unburied and use water-filled walls or special plastics for shielding transparently. For example, a greenhouse might be a dome with double walls filled with water, letting in sunlight but stopping radiation. By using local water for that, we leverage resources. Permanence on the Moon involves building infrastructure that doesn't need frequent Earth resupply. If we can harvest lunar water, grow some food, and manufacture building materials, a base transitions from outpost to settlement. Astronauts living there would shift from just surviving to thriving. They might plant hardy plants in lunar soil. Imagine a small lunar greenhouse with rows of leafy greens under LED lamps, a splash of life in the grey. One day, lunar settlers may cultivate the beginnings of a lunar society. Perhaps they start marking the passage of time differently. One lunar day, night cycle is a month, so they might have unique holidays at each full Earth to give hope during darkness, or at each sunrise to celebrate renewal. The concept of day and night is tricky there. At poles, perhaps they forget night altogether. Will they count time in Earth days or adapt to a lunar day of 708 hours? Likely they'll stick to Earth days for convenience with communications, but local timekeeping might develop for tasks. The Moon's low gravity is another interesting aspect. Astronauts on Apollo enjoyed hopping high and carrying heavy equipment more easily. Over long term, though, we don't know how human health fares in 0.16 G. It's more than microgravity, so bone loss and muscle loss might be slower, but it's still much less than Earth. Moon settlers may need robust exercise regimes and perhaps artificial gravity chambers. There's an idea to set up a short, radius centrifuge on the Moon for sleeping quarters, spin people gently at night to simulate full gravity on their bodies, allowing better bone maintenance. It might not be comfortable, but it's being studied. Nonetheless, the Moon's partial gravity could be a fascinating middle ground, enough to walk and keep some bodily orientation, but light enough to perform feats of strength and agility impossible on Earth. A child growing up on the Moon might become used to bounding meters high without fear, playing low gravity sports that Earth-born kids could only dream of. But if that child came to Earth, he or she might find our gravity oppressively heavy and struggle physically. We may see one day the ethical discussions about raising people in low gravity, knowing they might never be fully adapted to Earth. Permanence also means governance and routine. A moon base after a decade might have a rotation of crews like a scientific station, or might start keeping certain pioneers long term. Over time, they might form a council to manage resources, plan expeditions to new craters, coordinate with Earth, but increasingly make independent decisions due to their on-site expertise. The Moon is close enough that Earth oversight will be strong initially, but as the base grows to a settlement of dozens, a degree of autonomy likely blossoms. The identity of lunar inhabitants may shift, no longer just visitors, they become lunarians, with pride in being able to live in a place no human could before. They might develop an affinity for the stark moonscape, the black sky even at noon, the brilliant stars unblinking in absence of atmosphere, the sight of Earth hanging always in the sky. The Earth rise that wowed Apollo 8 astronauts isn't seen at the poles, but at equatorial bases, Earth would rise and set slowly over the month, a huge blue marble appearing and disappearing. Watching Earth set might be tinged with homesickness for some, but also a reminder of purpose. They are humanity's advance party, staying even when Earth is out of view for 2 weeks, proving we can endure off-world. A permanent moon base will likely accumulate the detritus of ongoing life. Old habitats might be repurposed as storage, spent landing vehicles turned into additional shielding, or cannibalized for parts. Over years, a sort of lunar town might emerge, with pathways worn in the regolith from frequent rover trips, maybe a little mound marking where the first flag and plaque were placed, now part of a larger complex. The base might honor that spot as a historical monument, even as they erect newer, larger structures around. There could be a cemetery one day, if someone chooses to have remains interred on the moon, a truly permanent resting place beyond Earth. All these are signs of moving from temporary exploration to true settlement. The moon's close connection to Earth means it will always be a bit of an extension of Earth, not wholly separate like Mars. Yet making a permanent human presence on the moon will profoundly change our species. No longer will all humans live on one world. We'll have a small population on another, living year-round, raising national flags, or perhaps a unified lunar flag, creating the first off-world community. They'll tackle everyday problems like how to fix a broken regolith excavator, or how to get fresh coffee when the Earth shipment is delayed. In solving these, they set the template for Mars and beyond. Someday, perhaps the moon base will grow into a moon village, with multiple habitats from different countries or companies near each other, connected by pressurized tunnels or frequent rover traffic. An international zone of cooperation on lunar soil, scientists sharing labs, tourists coming for week-long stays in special guest modules, mining operations selling propellant to passing spacecraft, maybe a radio astronomy outpost a short distance away on the far side. The moon could host not just one settlement, but a network of them, each specializing. One near a large ice deposit becomes a fuel factory. One at a peak of eternal light becomes a power station. One in a lava tube becomes a research park shielded from radiation by meters of rock. In all these visions, we see the moon transforming from a dead rock to a place of human footholds. Lights glowing softly at Shackleton Crater's rim, tracks leading out across the powdery desert to points of interest, radio voices chatting in multiple languages across the lunar network. And above any one base, if you step outside and look up, you see Earth, colorful, beckoning, full of life, a reminder of home and why you're extending its reach. Many lunar explorers have noted the profound emotion of seeing Earth from the moon's surface. It appears small enough to cover with your thumb held at arm's length, a fragile ball in darkness. That perspective might become routine for residents. They glance at Earth to check the weather patterns, or just as we glance at the moon from Earth. Maybe they have a saying like, "Earth's almost full tonight, beautiful and bright." The fragility of Earth will be obvious to them, likely instilling a strong sense of environmental stewardship and unity. After all, when you live on the moon, national borders on Earth literally disappear. You see the wholeness. Dust, light, and permanence. The moon will test our ingenuity with each. But where we solve those, we turn a forbidding environment into a second home. And as we plant roots there, even shallow ones, we become a multi-world species. The first moon base's success will be a signal that humans can truly stay somewhere other than Earth, not just plant a flag and leave. It will be one of our civilization's greatest milestones, the moment we go from sailing to a new shore to building a village there that can thrive through the changing seasons of that new world. Mars colonies, isolation, storms, and stability. When we imagine living on Mars, we conjure a vision of rust, red skies, sprawling dusty plains, and perhaps a small cluster of habitats huddled against the cold. Mars has captivated human imagination like no other planet. It is the world most like Earth in our solar system, yet still profoundly different. To establish a colony on Mars is to commit to isolation far greater than on the Moon, to face alien weather and planet-wide dust storms, and to seek stability and self-reliance in an environment that offers little mercy. It is, in a sense, the ultimate test of whether we can truly become a multiplanetary species. One of the most striking features of Mars is its isolation. At closest approach, Mars is about 55 million kilometers from Earth. At furthest, over 400 million. Even at light speed, messages take anywhere from 4 to 22 minutes to travel one way. This means a colonist on Mars who asks a question of mission control must wait perhaps half an hour for an answer. Effectively, they operate without real time support. Emergency on Mars. The crew must be their own first responders. Help from Earth would arrive, at best, months later, via supply rocket. The psychological effect of this distance is profound. Mars settlers will look up at night and see Earth as a tiny star, a pale blue point of light. There will come a moment, perhaps, standing under the Martian sky, when one realizes that everything familiar is a mere glimmer in the heavens. The emotional fortitude required to not feel crushing. Loneliness at that realization must be considerable. Yet, as humans often do, colonists will likely find ways to cope. Ritualizing communication sessions, fostering extremely tight, knit community bonds amongst themselves to replace the broad social network left behind, and cultivating a sense of purpose that justifies the distance. We have some analog in Antarctic winter crews who endure months of isolation and darkness. Mars will be that magnified, plus no immediate rescue possible. Crews on Mars will certainly deal with bouts of homesickness, interpersonal tensions from being in a small group so long, and perhaps an existential loneliness of being literally on your own world. In anticipation, our selection of Mars colonists will emphasize psychological resilience. Over time, as a colony grows and includes more people, that isolation lessens internally, but externally it remains. They are all isolated together from Earth. Eventually, a new normal sets in. Mars is home, Earth is the distant land. Children born on Mars might not feel isolated at all. For them, Earth might be an abstract concept, a beautiful star that their parents talk about. They may form a strong identity around their Martian homeland, bonding with their fellow colonists as one people in a way we haven't seen since perhaps early island settlers on Earth. The environment of Mars poses unique trials. Dust storms are iconic of Mars, vast clouds of fine dust that can engulf the entire planet. These storms can last weeks and obscure the sun, plunging the surface into a dim orange twilight. For a colony reliant on solar power, a global dust storm is a serious event. Energy rationing might be necessary unless nuclear reactors or massive battery farms are in place. The dust is pervasive. It can creep into machinery, abrade seals. The Martian dust storm of 2018 was so massive it ended the Opportunity rover's 15th-year mission by blotting out sunlight for too long. A crew on the ground would have to hunker down for possibly a month of low power, limited EVA, and carefully filtered air intake to avoid dust contamination. They might see the sky turn butterscotch brown and the sun become a feeble glow. Outside, the wind, though thin air, can still loft particles and slowly sandblast exposed surfaces. Colonists would design habitats with storm lockdown modes, shutters over critical windows, extra sealing on airlocks, and perhaps electrostatic repellents on solar panels or dust-resistant coatings. They might plan their heavy activities for clear seasons. The unpredictability of storms adds a psychological challenge. You could wake up to find the world has gone dark, and your carefully scheduled week must be thrown out to deal with nature's interruption. Flexibility and robust contingency plans are a must on Mars. Even when not stormy, Mars is cold and arid. Average temperatures hover around 60 degrees, though midday at equator can be a comfortable 20 degrees. The thin atmosphere offers scant protection from radiation or meteorites. Stability for a colony means building burrows or thick-walled habitats, likely underground or covered, similar to the Moon. Many concepts involve Martian lava tubes, natural tunnels left by past lava flows, as ready-made caves that could be sealed and pressurized. Imagine an entire colony built inside a cavernous lava tube. You'd have a rock ceiling 30 meters high shielding you, and you could construct habitats and greenhouses in relative safety. Mars has gravity 0.38 g, which is perhaps enough for easier mobility than the Moon, and possibly healthier long-term, but still, we don't know if 0.38 g is sufficient to prevent muscle atrophy and other issues. Martians might also need centrifuge habitats to simulate Earth gravity part-time. Over generations, perhaps humans could even biologically adapt somewhat to 0.38 g, but that's speculative and slow. Building a stable society on Mars entails getting beyond survival mode. That means reliable life support. Early on, Mars crews will eat mostly Earth, shipped food supplemented by some fresh greens grown in hydroponic trays. Over time, as they cultivate more, a larger portion of diet comes from local produce. Perhaps they'll manage small farming experiments in Martian soil. They might enjoy root vegetables, leafy greens, even Martian strawberries one day, grown under pink LED lights in climate-controlled domes. The first time colonists eat a meal made entirely from Martian, grown ingredients will be a huge milestone, a taste of self-sufficiency. Martian colonies must also deal with distance and self-governance. With hours of com delay round trip, they cannot be micromanaged by Earth. A certain autonomy is inevitable. We can foresee that once a group of humans has lived on Mars for, say, a decade, handling their own emergencies and decisions, they will start to feel Martian, not just physically, but politically. They might wish to govern their colony's affairs with less Earth intervention, not out of disloyalty, but practicality and identity. This parallels how remote colonies on Earth eventually sought independence or self-rule. The seeds of Martian societal culture will grow in those first enclaves. They might create new holidays. They may develop new art. Imagine dust drawings or sculptures from native rock. Music might be cherished in the long confined days. Perhaps someone brought a compact electronic keyboard or guitar, and evening gatherings include singing songs with new Martian lyrics about the landscape or longing for Earth. Over time, unique traditions will emerge. Storms and isolation may foster spirituality or philosophies tailored to Mars. In the extreme isolation of the Antarctic winter, crews sometimes report a heightened sense of fellowship or existential reflection. On Mars, this could be even stronger. There could be ceremonies before a long communications blackout, or communal readings of Earth literature to feel connected. Or something novel, perhaps stepping outside during a dust storm in a safe location to experience Martian night in a symbolic way. These cultural adaptations, small at first, lay the foundation for a stable society that's more than just surviving. It's living fully on Mars, with meaning and community. Loneliness will certainly be an enemy. Even a group of, say, a dozen, could feel claustrophobically small after a year together with no one else to see. Colonists will lean on technology, immersive VR calls with loved ones. Perhaps they'll have AI companions or robotic pets to provide some variety. They might maintain robust social schedules, designated game nights, shared cooking experiments. These efforts sound trivial, but they could be the glue that keeps spirits up during the monotonous stretches. The colony might rotate duties not just for fairness, but to break monotony. Everyone gets a turn at greenhouse care, at rover driving, at lab analysis, etc., preventing boredom and over-specialization stress. Mars also faces risk of cabin fever and interpersonal conflict magnified by isolation. To manage this, a Mars colony charter might include conflict resolution protocols, possibly trained mediators among the crew, or the ability to have private space. Over time, as populations grow, people will be able to find friend circles or get space from those they clash with, as happens in any town. The early crew of 4006 doesn't have that luxury. Later colonies of 50 plus will. If the colony endures through its first few tenuous years, it will accumulate improvements, larger greenhouses, an expanded habitat with spare rooms, maybe even the beginnings of terraforming on a small scale, like creating a pressurized dome with a garden where you can take off your suit. This wouldn't terraform Mars globally, but it creates micro-environments of Earth, like conditions to enjoy. Think of a Mars biodome as a park. Colonists could go in and smell moist air, feel grass underfoot, and have a picnic under an artificial sky of lights. Such an oasis could be mentally therapeutic, a stability factor for society. Mars' stability as a colony also involves economics. What will sustain it materially? Initially, heavy support from Earth, funded by exploration budgets or billionaire ventures. Eventually, the colony needs to produce value, be it scientific discoveries or facilitating further exploration. A stable Mars settlement might become a hub for the inner solar system trade, extracting useful minerals or manufacturing components in its lower gravity that are then shipped outward. If the economy stabilizes, the colony can grow, inviting more settlers because now it's not merely a cost center, but has industries. Family migration might happen. Perhaps a scientist brings spouse and children to live on Mars for a multi-year research project once the base is safe enough and voluminous enough. That moment, children laughing in a Mars habitat, will signify a colony crossing from expedition to community. The ultimate stability is generational. When the first person who was born on Mars grows up on Mars, knowing no other world as home, that person's identity will be Martian fully. The social dynamic then shifts. You have natives and Earth-born immigrants. Natives might adapt physically to Mars. They may see Earth as foreigners, albeit ancestral ones. It's easy to foresee a strong Martian patriotism or local pride developing. When enough people and infrastructure accumulate, they might declare themselves a Martian colony in political terms, perhaps seeking recognition not as under Earth nation jurisdictions, but as a new society. How that plays with terrestrial authorities will be interesting, likely new governance frameworks. Ethically, should Mars be an escape for humanity or a branch? These big questions will come into sharp relief when a Mars colony proves it's here to stay. Mars also offers unmatched adventure for colonists. They can pressurize rovers and drive hundreds of kilometers exploring canyons like Valle Marineris or climbing Olympus Mons. On rest days, some might venture out in pairs to examine odd rock formations or simply enjoy the horizon, with safety protocols, of course. The freedom to roam an entire planet can give a sense of frontier akin to early settlers on a continent. Over time, these explorers might set up secondary outposts, a mining camp here, a science station there, each seed a future settlement. That's how a colony expands stable, outgrowth and linking back. Maybe a base at a polar ice cap to harvest pure ice, or one near a volcanic region for geothermal energy. Throughout all, stability is about adaptation. Mars will change the colonists even as they change Mars. They will adapt routines to Mars's day, which is 24 hours, 39 minutes, only a little longer than Earth's. So we picture a Mars colony after a generation, a cluster of habitats at a site like Utopia Planitia, or near a large ice deposit. There are maybe 200 people. They have a town name for sentiment. Perhaps they call it Bradbury or Asimov, or an indigenous word meaning new hope. They have greenhouses providing a large fraction of their food. Diets lean vegetarian with occasional lab, grown meat, or insects for protein. They wear light indoor clothing, but always keep a pressure suit handy in case of depressurization emergencies. They have built radiation storm shelters underground, where they retreat during rare solar flares. They operate a fleet of rovers and even hoppers to reach distant locales. A handful of children play in a centrifuge playground that simulates Earth gravity, for exercise and fun. Education is mostly via digital content from Earth, but with local teachers adapting it. When the sun sets, the domed common area lights up with a warm glow. Perhaps the colonists gather for dinner in a communal mess, sharing news, a new baby born, a scientific breakthrough in the lab, the successful test of a new water recycling system that will allow more crops. Someone pulls out a guitar or a flute brought from Earth and plays a gentle tune. Others join in song or just listen, reminiscing about stargazing on Earth or plans for their next expedition on Mars. Outside, the wind may whistle and dust may skitter, but inside, it's shirt-sleeve comfortable and convivial. These people have carved out a stable life on an unstable world. Isolation, storms, and initial hardship have given way to routine and resilience. This colony is still tightly bound to Earth for certain supplies, but it's inching toward independence. They've even started making their own bricks and expanding living space without needing Earth shipments. Morale is cautiously optimistic. They are living the dream of many centuries, humans on Mars, and they feel the eyes of humanity on them. They have bad days, conflicts, homesick crying nights, technical crises, but they overcome them one by one. Each solved problem is a step toward not just surviving, but thriving on Mars. Someday, one of them steps outside on a clear dawn and watches the sun peek over the ruddy horizon. They see, faintly in the sky, a bright star, like dot that is Earth. At that moment, perhaps they realize, we are the ancestors of a new world. The storms will come and go. The isolation is real, but so is our community. And with each passing soul, Mars is becoming more stable as a human home. What was once a far-fetched science fiction scenario is now, under their feet, red reality, harsh and beautiful. And in their hearts possibly grows a fierce love for Mars, forged by facing its extremes. Just as people love their Earth homelands, from deserts to Arctic tundra, because it's theirs, so will Martian colonists love the rust and dust of Mars. In that love lies the true seed of a stable society, one that will endure and eventually flourish. Deep space, generation ships, and the dream of interstellar travel. Beyond the planets that circle our sun stretches the vast gulf to the stars. For ages, humans could only wonder what it would take to cross that unimaginable distance. Now, as we build habitats in orbit and envision colonies on Mars, a further dream glimmers on the horizon, voyaging to another star system. Such a journey would be measured not in days or months, but decades or centuries, far longer than a human lifespan. To accomplish it without breakthroughs in physics, we have conceived the idea of the generation ship. A self-contained world, carrying multiple generations of people who live and die during the voyage so that their descendants might one day arrive at a new sun and new Earth. It's a concept where science fiction edges into serious scientific discussion, because while daunting, it does not defy known physics, only engineering and human limits. Imagine a spacecraft, perhaps a few kilometers in length, a rotating cylinder or torus providing artificial gravity inside. It is essentially a miniature Earth, complete with gardens, water systems, and an internal sky. Such a ship would depart Earth with a population of, say, a few hundred or thousand, and an entire closed-loop ecosystem to sustain them indefinitely. The logic of a generation ship is straightforward. If we can't get there fast, we go slow and take our time with life continuing aboard. It turns interstellar travel into a multi-generational project, much like ancient human migrations, where those who set off never saw the destination, only their descendants did. The challenges are enormous. The ship must be practically self-sufficient in resources for centuries. This means near-perfect recycling of water, air, and nutrients. It must have reliable power, likely a fusion reactor, or a large solar sail catching distant sunlight. It needs to be shielded against cosmic rays, perhaps a magnetic field or heavy shielding, or both, because over a lifetime, cosmic radiation could otherwise severely harm the crew. Then there's the social challenge: how to maintain a stable society in a closed vessel for many generations. Humans in isolation can have conflicts. How to avoid destructive strife that could sabotage the mission. Perhaps a strong common purpose and carefully managed governance structure would be crucial. The crew's descendants must be educated in the ship's maintenance and in the mission goal, so that by the time the ship nears a target planet, they have the knowledge to land or settle it. The culture aboard may evolve in unforeseen ways. They might develop new religions or philosophies about their unique existence. They might even forget Earth if records were lost, or deliberately reinvent their history. There's a well-known fictional trope of generation ships that lose knowledge of being on a ship. Realistically, we'd guard against that by ensuring continuous education, and maybe having parts of the ship transparent, so people can always see the stars outside and remember they are on a journey. In fact, imagine stepping to an observation dome on a generation ship. Outside is not Earth's blue sky, but the black of interstellar space, studded with ancient light. The stars barely change position over decades, though the destination star gradually brightens over generations. To the people on board, those stars are their night sky, constant and comforting. A generation ship would likely depart slowly from Earth, maybe assembling in orbit or near the moon. Families and skilled individuals would board with solemn farewells, knowing they will never return and possibly never even see the new world. But their great-grandchildren might. It is a massive leap of faith and commitment. Perhaps they are driven by necessity or by pure exploratory zeal, a willingness to sacrifice personal horizon for the species' expansion. During the voyage, life on a generation ship might in many ways echo life on a large space colony, with agriculture, work, birth, death, art, and routine. They'd celebrate their ship's anniversaries as we celebrate national holidays. There would be time to pursue studies, hobbies. After all, in a self-contained town, traveling in darkness, cultivating culture is vital. They might develop unique art forms suited to weightlessness or confined space. Perhaps zero-G dance performances in a central hub, or music using instruments crafted from spaceship materials. Over centuries, their language might drift from Earth's, picking up spaceborne slang and technical vernacular, becoming a dialect or even a distinct language by journey's end. Anthropologically, a generation ship is a fascinating petri dish of society. Small, isolated, forced to be self-reliant and balanced. Social engineers might, when launching, try to include a broad genetic and cultural diversity to avoid inbreeding or cultural stagnation. The early crew might have multiple languages, beliefs, traditions, intentionally, so that the future culture aboard is rich and adaptive, not monolithic. Because a homogeneous group might handle conflict resolution worse or could face genetic issues down the line. So, one imagines the ship launching with couples and families from many backgrounds, all united by a mission charter, somewhat like the US Constitution, a guiding document that lays out rights, responsibilities, and conflict resolution methods for the community that will persist long after the original authors are gone. Technologically, generation ships flirt with extremes. Speeds of a few % of light might be attainable with advanced propulsion. Even then, reaching Alpha Centauri at 1% of light speed takes about 437 years. If they average 5%, it's 90 years, possibly within one long lifetime, but more likely spanning 3 or 4 generations. Many proposals consider hundreds of years voyages. This demands reliability far beyond any machine we've built. Perhaps the ship will have onboard manufacturing to replace or repair parts. It essentially must be a self-healing system or carry massive redundancy. The voyagers might also enter stasis or sleep to shorten perceived time. But generation ship concept typically assumes they remain awake and society continues. Interestingly, the generation ship idea, while heavy on logistics, is also inherently hopeful. It assumes that even if individuals can't reach a goal, the chain of humanity can existential hope and insurance for humanity. Stephen Hawking and others argued that, to ensure our survival, we eventually must spread to other star systems. Generation ships could be our way to do that, with known physics. They are effectively space-going Noah's Arks, carrying not just humans, but seeds, embryos, knowledge, possibly even animals to plant life elsewhere. It's a massive undertaking, building a world to travel between worlds. As of now, this remains theoretical. The farthest humans have gone is the Moon. Even Mars is still ahead. But as we master each step, orbital living, lunar and Martian bases, the generation ship idea moves from wild idea to distant but conceivable project. Already groups like Icarus Interstellar and the Initiative for Interstellar Studies have begun research on how to design life support and propulsion for such century-spanning missions. It might be a project of a civilization, not a single country, something humanity collaborates on when we feel confident enough in our space capability and united enough in purpose. Perhaps a future Earth that is sustainable and peaceful might devote some of its energy to launching world ships to nearby stars. What's inspiring is that generation ships treat life itself as the Voyager. It's not a quick heroic exploit by a few, but a commitment of an entire living community to journey together into the unknown. In a sense, it's a continuation of the earliest human story. Tribes migrating across continents, not knowing what's ahead, but believing somewhere fertile and safe lies beyond the horizon. Only now, the horizon is interstellar space, and the journey dozens of lifetimes. It asks, can we create meaning and maintain society in the ultimate closed bubble? If the answer is yes, it affirms a wonderful adaptability of humans, that we can find home even in the journey, not just the destination. So while generation ships remain for now a bold speculation, they encapsulate the enduring human traits of wanderlust, patience, and hope. One day, a child might be born in the midst of such a voyage, never having stood under an open sky, yet that child may live to step onto a virgin earth under an alien sun, fulfilling a dream begun many generations before. That prospect, that we might traverse the cosmic ocean as families over epochs, gives a sense of how far our will to explore could truly take us. It lets imagination orbit physics, daring to plan for futures far beyond our personal lifespans. In this way, generation ships are both engineering challenges and profound statements of optimism, an implicit faith that humanity will endure and carry forth its flame of life to new worlds among the stars. Terraforming, reshaping worlds. If one day we stand on Mars or another barren planet and yearn not to be confined to domes and suits, the thought arises, could we transform this world to be more like Earth? Terraforming is the grand idea of planetary engineering, modifying an entire planet's environment to make it habitable for Earth life. It is an idea at the intersection of high science and audacious imagination, because it implies taking what nature built over eons and tweaking it intentionally on a massive scale. The most discussed target is Mars, since it has water ice, some CO2, and was possibly warmer eons ago. The dream, thickening its atmosphere, warming it, and perhaps even seeding it with life, so that future generations might walk on Mars without a spacesuit, under a blue-ish sky with flowing water around. But how feasible is this, and what are the ethics? Mars today has an atmospheric pressure less than 1% of Earth's are, too thin to breathe or to allow liquid water stable on the surface. It's also cold. The basic terraforming plan would be to pump up the pressure and heat by releasing greenhouse gases, mainly CO2, which Mars has locked in polar ice caps and soil. If we could vaporize the poles and some CO2 from the soil, we'd create a thicker atmosphere that could trap more heat. Some scientists once thought there was plenty of CO2, but recent studies, including findings from NASA's MAVEN orbiter and Mars Express, indicate Mars simply doesn't have enough accessible CO2 to do the job. If you sublimated all known CO2 on Mars, you'd get only perhaps a 15 from 30 mbar atmosphere. That's nowhere near enough for humans or to significantly warm the planet. A 2018 Nature Astronomy paper concluded that there is not enough CO2 remaining on Mars to provide significant greenhouse warming where it released. Even massive future efforts would result in only a fraction of the pressure needed. In short, current research puts a damper on classic terraforming. Mars is too CO2, poor to be easily terraformed with present tech. That doesn't make it theoretically impossible, but it means we'd need more exotic methods. For instance, importing volatiles, crash comets full of ammonia or water into Mars, or use super powerful factories to create synthetic greenhouse gases. These ideas involve titanic scales of energy and time. Smashing a few hundred comets into Mars might deliver enough gas and water, but guiding comets safely is science fiction. Level for now. Manufacturing an atmosphere would require literally covering Mars in factories running for perhaps centuries, outputting gas. Assuming we somehow succeed in raising the pressure to something like half an Earth atmosphere and temperature to near 0 degrees average, we'd then consider biosphere introduction. Initially, we'd have a mostly CO2 atmosphere. Humans still couldn't breathe that. It's for plants and microbes. We might sow the planet with hardy pioneer life, genetically engineered algae or lichens that can tolerate cold and high UV to start producing oxygen and creating soil. Over long spans, these could build up O2. Earth took billions of years and specific conditions to get an oxygen-rich air, so expecting a quick oxygenation is unrealistic. It might take millennia or require further intervention. Another approach to terraforming is more localized, paraterraforming. Instead of trying to change the whole planet at once, build large enclosed regions, e.g. giant domes or even crater, wide transparent canopies, and terraform inside them. This is more achievable near term. You could seal off a large crater with a strong clear roof, then pump air inside, seed water and life there. That crater would become a shirt-sleeve valley, perhaps tens of kilometers across, where earth plants grow in Martian soil under a controlled climate. It's like creating big oasis patches on Mars. Over time, you enlarge these patches. This is not full terraforming, but could make sizable areas habitable relatively sooner. The ethical side: if Mars harbors any native life, do we have the right to alter the planet and potentially destroy that biosphere? This is a serious concern. Planetary protection protocols currently forbid intentional contamination of Mars until we're sure no native life exists, or until we decide to override that. Many argue we should thoroughly search for Martian life first. If Mars is sterile, terraforming is a grand extension of life. But if Mars has even a simple biosphere, terraforming might obliterate it, which some would view as unethical and hubristic, ending an alien ecosystem for our own ends. Possibly a compromise, if Martian life exists, maybe confine terraforming to regions without it, or even attempt to include Martian life in the terraformed environment. Beyond Mars, people talk about terraforming Venus, cooling it down, removing its thick CO2 atmosphere, but that is an even more Herculean task. Or terraforming moons like Titan. Some speculative future tech, like redirecting asteroids or even altering orbits, enters these discussions. For instance, one wild idea: send large mirrors or lenses to focus extra sunlight on Mars to heat it, essentially an artificial greenhouse effect via orbiting mirrors. Conversely, for Venus, put a giant shade at Sun, Venus-Lagrange point to cool it, and then perhaps bombard it with hydrogen to lock up CO2 into rocks, colossal geoengineering beyond current reach. Time is a factor. Terraforming is slow. Even optimistic scenarios see centuries to thousands of years to get a breathable Mars atmosphere. That's a timeline that dwarfs human political cycles and maybe attention spans. It raises practical questions. Who begins a project that none of their great-great-grandchildren will live to see completed? It requires a civilization committed long-term, or an automated process that runs without much oversight. A possible path is that once we have colonies, they might incrementally terraform for their own expansion, not a formal global terraforming plan, but by making larger safe zones over time, they in effect terraform bits of Mars which eventually merge. One might also ask, should we terraform at all? Some argue leaving Mars as is, a natural reserve or science lab, is better, and humans can adapt to Mars via technology rather than adapting Mars to humans. Others feel giving Mars a biosphere would be giving it life and purpose, a grand altruistic act to spread Earth's richness. In fiction and futurology, a fully terraformed Mars is depicted with flowing rivers, blue patches of sea in its northern basin, forests in valleys, essentially a second Earth with rust-colored rocks and maybe pink skies. Perhaps most appealingly, it's a future where humans can stand on another world and breathe freely, having literally reshaped a planet to suit life's needs. This is an ultimate expression of life becoming a force of nature beyond Earth. Even if we conclude classical terraforming is currently beyond reach, the pursuit of it teaches valuable lessons about planetary climates, even Earth's. Already, studying how to warm Mars sheds light on our warming Earth. The magnitude of Mars's CO2 deficit relative to needs also humbles us. It shows how special Earth is to have the right air, and how difficult it is to replicate that elsewhere. Terraforming talk leads to philosophical perspective. It's playing creator on a planetary scale, something far beyond any collective endeavor we've done. It requires both incredible technology and nearly spiritual will, a devotion to making a dead world living. Time, patience, vastness, these become tangible factors, tying into the earlier theme of slowness and patience in space travel. Perhaps terraforming, if it ever happens, will be done by our distant descendants with powers we can't yet wield. Or perhaps we'll choose gentler terraforming, sustaining bubbles of life in hostile places and gradually enlarging those. Either path, the notion that we might reshape worlds is a testament to the human blend of audacity and creativity. It pushes the boundary of home beyond Earth, not by adapting ourselves to every environment, but by also adapting environments to us. It's a form of cosmic gardening, with planets as the canvas. In the far future, if we overcame the obstacles and Mars stands verdant, what a legacy that would be. Imagine travelers from Earth arriving on a terraformed Mars centuries hence. To them, it's a vibrant world. They might not fully appreciate that once it was barren, and it was human effort that greened those plains. But perhaps plaques or monuments would dot the Martian parks. In memory of the terraformation, begun 2250 AD, completed 2700 AD by the peoples of Earth and Mars. The ethical debates would be settled by history. Martian life would now be abundant, though imported. Earth trees, Martian, evolved descendants of Earth microbes, maybe even animals if they were eventually introduced in controlled refuges. It would be a second cradle of Earth life. It would be a second cradle of Earth life on a once barren world. A living monument to human creativity and persistence. The red deserts would have blooms of green, and a future traveler might forget that Mars was ever uninhabitable. The story of that transformation would be told in school books, how humans became, in effect, the gardeners of planets. Yet we must temper this vision with humility. Terraforming is no simple panacea. It's an extreme undertaking that could span millennia and demands wisdom. As one study concluded, there is not enough CO2 remaining on Mars to provide significant greenhouse warming with known methods. In other words, we can't just push a button and give Mars a breathable sky. The raw materials aren't readily there. This reality check teaches us to cherish Earth's perfectly tuned environment even more. Our planet is a rare jewel, all the ingredients for life in just the right balance. In attempting to emulate that elsewhere, we appreciate how complex and precious a biosphere is. Perhaps the greatest lesson of the terraforming dream is the reinforcement of environmental stewardship at home. If we ponder greening Mars and see how hard it is, it may motivate us never to let Earth go barren by our own folly. In the end, whether or not humanity ever fully terraforms a planet, the act of trying, even on smaller scales, will mean we have grown into a role of cosmic custodians. We will have moved from simply living off the land to literally reshaping worlds to support life. That is a profound responsibility. It forces us to decide what values to carry into the cosmos. Do we preserve alien nature as we find it, or do we spread the life we know? There is no easy answer. Perhaps the answer will differ case by case. Mars might become new Earth, while another world we might leave untouched as a scientific preserve. Our descendants might look back at these early debates as the first ethical steps toward becoming a multi-world species. For now, terraforming remains a distant aspiration. But in laboratories and computer models, we tinker with the ideas, learning how atmospheres work, how greenhouse gases warm or cool. This knowledge loops back to help us manage Earth's climate. In a sense, by dreaming of terraforming Mars, we are also discovering how to re-terraform Earth if needed, to undo some of the damage we've done with climate change or ecological destruction. Learning to shape a harsh planet into a livable one might teach us how to keep a livable planet from becoming harsh. Terraforming thus embodies both our ambition and caution. It is the ultimate expression of letting imagination orbit physics, as we attempt to make imagination into physics, turning what is into what could be. Whether it takes 300 years or 30,000, the thought that one day a distant world could be alive with Earth, descended forests and oceans, is a powerful beacon of hope. It suggests that life is not chained to its cradle, but can spread and blossom anew in the cosmos. In that sense, successful terraforming would be like life itself, planting seeds in new soil, carrying forward the legacy of our home into the wider universe. Artificial ecologies, gardens in orbit, and biophilic design. Across all these ventures, stations, bases, ships, and new worlds, one thread is vital. We need nature with us. Humans evolved among rustling leaves, flowing water, and other living creatures. Our minds and bodies crave those cues. The sterile metal walls of a spacecraft, however advanced, can never fully satisfy the longing for green growing life. Thus, wherever we go, we bring pieces of Earth's ecology and attempt to weave them into our habitats. From a small potted plant floating in a space station window to entire biodomes on Mars, biophilic design will be key to making space homes feel like home. We have already seen the impact of tiny gardens in orbit. The ISS crews have tended little patches of zinnia flowers and lettuce in microgravity as part of experiments, and they report how seeing a bit of green and orange bloom amidst the machinery lifted their spirits tremendously. They also very much like growing plants. It boosts morale and provides fresh oxygen and smell, notes one Canadian Space Agency article. Indeed, astronauts have said the scent of fresh flowers or herbs in that recycled air environment was almost magical. These are artificial ecologies in miniature: a small rooting pillow of soil, LED lamps replicating sunlight, water delivered carefully so it doesn't float away, a whole life system engineered into a box. And yet, the result is real, a living organism sharing the habitat, responding to the care of the crew. It's a preview of what larger green spaces could do. In future orbital stations or lunar Martian bases, designers are already planning dedicated green modules or plant walls inside habitats. A hydroponic wall of climbing plants or a central atrium with a few trees under an LED skylight, could drastically change the ambience of a confined base. Instead of purely synthetic environment, one would wake to the humid freshness of leaves transpiring moisture, maybe even birdsong. Biophilic design has proven benefits: reduced stress, improved mental well-being, even better cognitive performance. In a Mars base, a greenhouse might double as both food source and psychological refuge. Colonists might go there off-duty to sit among the plants and feel a semblance of Earth. One can imagine a Martian park in a pressurized dome, complete with a little pond and a bench by it, where one can go meditate under the light of a simulated sunset. These artificial ecologies aren't just decoration, they become functional parts of the life support loop. Plants regenerating oxygen and consuming CO2, maybe providing some food. In essence, we create a self-sustaining garden within the technology, each supporting the other. Engineers consider things like which plants are best: sturdy, low, light-tolerant, high oxygen output, or edible. Possibly future habitats will favor multi-purpose plants. There's even talk of genetically engineering plants specifically for space. Maybe a super algae that is extra efficient at scrubbing air, or dwarf wheat with higher yields. But beyond utility, will also include plants just for beauty and comfort. A rosebush on Mars might not feed anyone, but the first Martian, born teenager, might gift a rose grown in Martian soil to their sweetheart, a gesture that ties human emotion to this new world's nature. Biophilic design goes beyond plants. It means using natural materials and forms so inhabitants feel less machine, encased. Windows to space count too. Seeing the Earth, Moon, or stars can instill awe. But overall, opening views, curving shapes reminiscent of natural forms, and warm natural colors can make a station more psychologically livable. Future architects might model habitats after seashell spirals or cellular lattices, shapes our brains find inherently organic. This is already an earthly trend in architecture. Expect it to be even more valued off-world. There's also the concept of creating closed ecosystems for research and pleasure, like a small pond ecosystem in a bubble, where fish, plants, and microbes form a cycle. On Earth, experiments like Biosphere 2 tried to enclose ecosystems. They hit difficulties, but in smaller scales and with continuous management, they can work. An orbital station could have an aquarium tank with fish, not just for decor, perhaps also for protein food source. Astronauts have expressed joy even from simple life, like watching brine shrimp or insects they brought along. The movement of other living creatures breaks monotony of human-only company. Artificial ecologies also teach us about sustainability. If we learn to keep a little garden alive in space with limited inputs, we learn how to be efficient and balanced, lessons directly transferable to Earth farming and vice versa. The plants grown in microgravity have shown us how life responds to conditions utterly different. This knowledge expands our understanding of biology. How adaptable is life? We see that with a bit of help, it can survive even off Earth. There's a poetry, too, in carrying seeds across space. Consider a scenario. On a generation starship, an elder might pass a precious heirloom seed to a grandchild. This is a cutting of the oak from our ancestral home. Plant it when we reach the new world. That act symbolizes continuity.